Good morning and welcome to this year's Pollution Forum at WWEM. My name's Oliver Grievson and I'm going to be your host for the day. I think it's fair to say that pollution has been very much on the agenda at the minute. A lot of you I know will have watched the Environment Audit Committee yesterday afternoon or perhaps last night on re-record like me. And I think to say pollution is a very live issue is an understatement. It's a very serious problem. The quality of the rivers are of massive importance. And we saw that yesterday, the CEOs of 5 of the water companies absolutely saying, let's sort this out. Let's do things. Let's get it sorted. And so there's that appetite to sort things out, to work together, to collaborate, to sort this problem. Today, we're very much going to be talking about measurement. The whole theme of the WIPAC forums this year, the 2 forums and 2 roundtables, have been why do we measure? We've all heard the old adage of measure to manage, and it still works nowadays. It worked when it first came out. I don't know how many years ago. It still works now, but we've got to temper that with what can we actually do? Why are we measuring? And it's an important question that we're going to speak about in the first session. Why do we measure? What's the point in measuring? Well, yes, it's to manage. Yes, it's to find out the situation that's going on. The water industry has always been accused of being data-rich, information poor. By adding more measurement, are we going to solve that? Perhaps. How do we get the most bang for the buck, for the environmental buck? And that's a question I really want to take today. And how do we use measurement? How do we use the management through measurement? And how do we use digital transformation in some ways to really solve the pollution problem? So I'm going to stop waffling on and I'm going to introduce our first speaker, who's Dominic Shepherd from the Environment Agency. He's the water quality manager there, and I've known Dom through the flow work he's been doing with Pete Baker and the water companies, and great stuff. But I'll let Dom talk about the need to monitor. Dom, take it away.
Brilliant. Thank you, Oliver, and thank you everybody for inviting me along to talk today. A little bit about myself. I've been with the Environment Agency and prior to that, the National Rivers Authority for nearly 30 years now. Before that, started for a short spell just after I left uni with Northumbrian in asset. I think we were doing some asset surveys for AMP1. It was my first ever job in the business. Mostly it's been around environmental planning and regulation, but increasingly monitoring, in particular around pollution regulation, has become part of my role. As Oliver's mentioned, the wastewater flow-to-full treatment monitoring program that we're doing, I lead that for the Environment Agency and have worked closely with the companies and with Oliver on that. But also I'm involved with leading our response to EDM, event duration monitoring at storm overflows, on the compliance side of things. So Keith Davis, who some of you may know, leads on the planning and development and investment side of things based on EDM, but I lead on the compliance side of things. I think the amount of monitoring we do is greater than ever before, but the need to monitor even more is greater than ever before. And that's what I'm going to talk to you about today. So next slide, please. So why monitor in the first place? Well, things are changing. Population and economic growth is increasing the demand for natural resources, for food, for housing. We're creating more infrastructure, and in turn, that's putting much more pressure on the environment. As we are all well aware, the climate is changing. The Environment Agency's 3rd adaptation report under the Climate Change Act was published this week, and it includes quite a lot about predictions for high and low flows. This will seriously affect how we plan for the environment, for pollution management, and for regulation. We'll be looking at tightening standards just to protect the gains we've made. Environmental performance is pretty static, if I'm honest, and in some cases is deteriorating. Pollution incidents across all sectors are on the rise, slightly static in some, but for the water industry, particularly on Cat 3s, we are seeing an increased number of incidents. We're already doing more monitoring, and actually that in itself is telling us more about compliance and non-compliance. For example, the EDM monitoring, the event duration monitoring, we know that there's an awful lot of storm overflows that are discharging in dry weather. We didn't know this last year. You'll have seen in the media recently about pollution. Panorama, Country File features it. There's an ITV programme being filmed tonight about pollution. And we're being quizzed at the EACs, which Oliver's already mentioned. Our chief exec, James Bevan's been there. The company chief execs were there yesterday. A massive amount of time is taken up by our technical staff and your technical staff in the companies and in the supply chain and consultancies in helping managing the reputation risk. And this actually is affecting us. It's preventing us in some cases from doing our job, which is about protecting and improving the environment. So much time has been taken up by managing the reputation risk. Monitoring is key to these pressures, and it's there to help inform cost-effective solutions, sustainable solutions, track performance, and provide the public the assurance that we need and the assurance that we are doing our jobs properly. The need to monitor is greater than ever. Next slide, please. So, traditional monitoring. Where have we come from? This is what we've done largely in the past, but not in the. This is what we were doing when I first started in the business, and up until about 10 years ago. EA took the compliance samples as well as did all the environmental monitoring, the surveillance one, the GQA as it was then, the RE reporting, and then latterly the WFD reporting. Mostly it was about, for compliance side of things, it was chemical sampling for board, ammonia, suspended solids, the sanitary parameters, but also for metals was a common thing we looked for. Environmental monitoring was a bit more involved. We've done biological sampling, and we've also done chemical sampling and sampling for macrophytes for some time now as part of our classification of water bodies. Occasionally we've done some composite sampling, urban wastewater treatment. Probably the first time we got the water companies to self-monitor. But, traditionally we didn't do much in the way of self-monitoring or continuous monitoring at all. And I suppose the question was, well, is 12 spot samples at a wastewater treatment works each year really enough to tell us what's going on? So, if I move on to the next slide, please. So, if we're looking at slide 4, which is our current approach, we've moved a long way over the last 10 years. We've shifted to OSM. We do UV disinfection monitoring, self-monitoring. We monitor dry weather flow, and that's reported. And we've recently put EDM monitoring in at the sewage works, or required EDM to be put in at the sewage works. We're moving forward with the programme of FFT monitoring at around 3,500 sewage works, which Pete Baker talked about yesterday, and I'll touch upon later. But actually in the environment, there's been no real change. Environmental service surveillance monitoring is still largely done by us as the regulator and in the traditional way. Interestingly, the public and EGN, environmental NGO pressure is for EA to do all of the monitoring, because there's mistrust about self-monitoring and reporting, and this featured heavily in the quizzing at the EACs, particularly from the ENGOs. That's not our belief. I strongly believe in a combination of OSM, us doing some checks and audits, and then the development of new monitoring, new innovative techniques such as the EDM and the flow monitoring, and indeed we'll look to the future later in the presentation. But this gives us a much better, much more comprehensive picture, but we need to work on the reputation and the understanding to help the public and the pressure groups and the ENGOs understand this. So next slide, please. So a bit of an example. This is the EDM monitoring that's gone in. We are hoping to have, or will have, full coverage of EDM at storm overflows, which monitors the length of time a storm overflow is discharging and when it discharges, and that's reported annually. We'll have full coverage by 15,000 overflows by 2023. We've currently got about 12,000 overflows monitored. That's 80%. And that's already driving a lot of investigations. We've got 700 investigations going on into frequently spillers. We are currently doing a lot of compliance investigation around the returns. It's also informing the DEFRA-led Storm Overflow Task Force. So this is where we're using the data to inform planning and legislation such as the drainage and wastewater management plans and the Environment Bill. It's underpinned a lot of the thinking around wastewater planning in the Environment Bill. Next slide, please. I hope people can see this. This is just a summary of 2020 EDM data. I'm not going to go into any detail, but there's lots of things you might expect. We get more spills in the northwest. No surprise there. It rains a lot. But it does show some oddities. And to the layman, this might seem very odd. For example, if you look at the Thames spill numbers, the average spill number and the spill duration of Thames overflows is greater than pretty much anywhere bar the northwest. The devil is in the detail, though, and this is the part of the helping people understand is how many overflows have Thames got, where are they in the network. You know, I don't think it's any reason to be alarmed. It's just they have less overflows further down the networks, which is leading to these figures. This information is great for planning and useful for compliance, but what it has driven is a massive increase in public and political awareness, and that's leading for calls to minimise or even eliminate storm overflows. So it's having a massive impact. It requires an awful lot of work for us to help manage this understanding, but it's also illustrated where we need to do a lot more work to reduce discharges in the future. So next slide, please. Another example, this is flow pass forward. Pete Baker talked about this yesterday, so I'm not going to go into a great deal of detail here. But this is the programme that I'm leading for the EA. About 5 years ago, we asked the question, what do we really know about FFT? It's a permit condition, but do we really regulate it? And it was triggered by some strange things we were finding, such as depressed ecology downstream of wastewater treatment works, you know, which we thought really shouldn't be there. There was no reason for that. There was no other pollution source. The fine effluent was fine, and so on. I mean, that triggered some local investigations, some of which have just concluded recently, and indeed triggered some significant enforcement action. But it also led us to think about, well, what do we need to do to get a better handle on this? So working with the industry over the last 5 years through the FFT Flow Task and Finish Group, we have got around an £80 million worth of investment, so that we're going to get 3.5 new FFT monitors and spills into storm tanks, EDM spills into storm tanks. put in by the end of this AMP, with a little bit of carryover into the next. This will give us a much better picture of FFT compliance. It will give us a picture instantaneously if we need it, what's going on, but it also allows us to do annual compliance tests. This information, we expect, when it comes through, will drive a lot of investment in FFT over the next 5, 10, even longer years, as we understand FFT compliance much more. It also will give us the public confidence, so it's that we are monitoring FFT. Currently, we're coming under a lot of criticism about this. So next slide, please. So the benefits of improved monitoring. What's not to like, really? Improved compliance. We measure it so we can manage it. It highlights where we need to do more, hopefully in advance. And it also means that we can hopefully avoid pollution and minimise risk of it occurring in the first place. It also then minimises the risk of enforcement action, so it's worth the investment. If we can monitor and predict what's happening, then we can minimise the risk of non-compliance and enforcement. Rolling better planning and optimisation and efficiency in together. Monitoring maximises the opportunity to target investment, optimise performance where it's needed, and to avoid abortive spend where it's not. In future, I hope that it can start to drive more innovation and sustainable solutions, especially to meet the climate challenge. Lastly, increasing transparency gives the public confidence, and we use it already, and I think we'll be using it a lot more in the future. But one of the great examples is we use EDM information together with rainfall radar and other information in our pollution risk forecasting, which gives us information which allows us to warn bathers when there might be poor water quality. And this has been a really successful of using monitoring in real time as part of a wider package to the benefit of the wider public. Next slide, please. So, we as a sector and as the regulator are losing what the new EA Director of Water, John Leyland, is calling the media air war. It's EDM monitoring, WFD classification, and soon FFT monitoring, which is driving the unprecedented ENGO media interest and political interest. There's far greater expectations, such as the demand for rivers to be of bathing water quality, as we've seen in Ilkley and Yorkshire, and there's a number of different schemes going on there. There's some very sophisticated pressure groups, such as WASP in the southeast, but they're now acting around the country. That's the Windrush Against Sewage Pollution, are using the data that we are collecting and providing to them to influence policy and legislation and highlight their agendas. It's taking up an awful lot of time to manage this. And as I said before, it can detract from actually trying to fix the problem in the first place. But it is capturing the political imagination, and it's really this which has driven the EAC. Monitoring not only highlights the problems, but it can provide the solution. So it can show progress, it can show things are moving forward and getting better, and this is what we need to do in terms of this media air war. We need the pressure groups, we need the ENGOs, but we also need to help them understand the complexities of monitoring and the data and how it should be used to help us in the long run. Next slide, please. This is the long run. The Environment Bill, looking to the future, includes big sections on monitoring for pollution. It reflects the political and public demand for more data and on discharges and their impacts. There is a switch from the tradition of EA doing all the monitoring in the water environment in terms of surveillance and such like. We'll still do surveillance monitoring. We'll still have the primary role there for WFD reporting and so on. But increasingly there will be a greater emphasis on water companies using continuous monitors, upstream and downstream of discharges, that's CSOs or storm overflows, and continuous discharges, to assess the impact of those individual discharges, and then scaling that up to see what the collective and the cumulative impact is. There's also a requirement in the bill for companies to publish what they're calling near real-time information on storm overflow discharges. So this is pretty much what we're doing already for pollution risk forecasting and such like in the SwimFo apps. But within about an hour of receiving the data, the expectation is that we will be publishing this on the website. Whether that stretches into the upstream and downstream monitoring data, whether we need to live stream that and things like that, then that's a big challenge for all of us. Logistically and practically, it's going to give us a real challenge, but if we get it right, it can provide some incredibly useful information and help us reduce pollution in the long run. Next slide, please. So, to summarise, the need to monitor is there. It's required by legislation, it's demanded by the public, and most importantly, it's absolutely essential if we're going to meet the challenges and maximise the benefits for the environment. Next slide, please. And that's the end of my presentation. Thank you for listening, and I'll open it up for questions at the appropriate time.
Thank you very much, Dom. Very, very interesting stuff there. And even from an instrumentation, I must admit, I've been ambiguous on how much we need to monitor, because some aspects of it, to be honest, worry me. But I think we'll come on to that. I think we'll bring Lee on and we'll bring Ian on and have a bit of a round table discussion at the end, because I think all three presentations this morning kind of talk at the same subject from different areas. So, Lee, do you want to take over?
Yeah, thank you very much, Oliver, and thank you very much, Dominic, as well, for a great talk. First thing. So very, very quickly, I'm Lee Upton. I am currently a environmental advisor for South West Water. I've been in the water industry since '98. Joined Severn Trent Water. I was a biologist and did a lot of process support work there. I then went to the Environment Agency, was an environment officer and environmental crime officer. Went to Severn Trent Services, which is looking at the MOD contract, which is a slightly different client base with very, very old infrastructure, which is some of what I'm going to talk about in this. And then I have moved to the Southwest, the beautiful Southwest, and working down there on minimising pollution. So very quickly, that's me. So if we can move on to the first slide, please. Okay, so what I'm going to talk about is sort of how the water industry, in very, very broad terms, looks at the monitoring that we do. So I've got a bit of a risk matrix down there, not the standard risk matrix, but it's against the amount of monitoring that we do and the types of monitoring against the risk that we cover. So that could be risk to the environment, partly based on what the Environment Agency think that risk is. So the types of permits, things like that. The risk to the company of actually staying within that permit or inside that permit, the company reputation, things like that. So that's the risk building. There's also the cost element, cost of putting in new equipment, maintaining the equipment, the manpower needed to run those sites, the training requirements. There's a lot of things that goes in there. And also there's a reputational bit there about gathering more investment for companies. If we're not doing as well, we might not be seen as well. The last bit there with location. sort of sits between the two. So location could be manpower, long distance, long travel times, things like that. Access issues, if it's difficult to access a particular asset, but also where it's located. Is it upstream of a triple SI? Is it on a bathing water? Is it on shellfish water? All of those things add into that risk matrix. So that was just an overview of where we are, and we're going to look at sort of the basic, the monitoring, and then monitoring control and how we put that in. So that's the green bits. The amber is where we will use them at the right time. And the one little red one up there is that we're probably not going to use that apart from some very, very specific circumstances. So we can move on to the next slide, please. So this is what we're deeming our small sites. So we're looking more at our descriptive permits at the moment, generally only domestic sewage, no industrial, shouldn't have any real industrial stuff in there. So a small population equivalent, package plants, small filter works, but not terribly complex, and generally old, tried, tested kind of equipment. So we do basic monitoring. It is on-site tests, turbidity tubes, ammonia test kits, and one that is overlooked, I think, quite a bit, which is observation by operators. When they go on site, they'll notice smells, sounds, changes from the norm is the best way to put it. Has the colour of that effluent changed slightly? Has the smells changed on site? And all of that, which is generally difficult to quantify into electronic information, but it will be recorded. There might be other bits and pieces depending on where it is. So they might need pH or DO control monitoring on site, and that would be generally handheld. There will then be only critical asset monitoring. So if we're looking at RBCs or filters, we're really looking at loss of rotation sensors, that kind of thing. Anything that, if it breaks down, the process stops. And that will generally be it for these kind of works. Obviously, if it's aeration, we're looking at blowers, and we probably have, if it's a powered site, a loss of power kind of monitoring alarm that says we've got a problem here. The recording and monitoring of the data is very, very basic. You've only got those signals coming off. Any other information is what is recorded by an operator, probably in text. So it's not terribly easy to get that information out and use it in a really useful kind of format. And that data is rather limited. So your small sites, your descriptive sites, are not going to be visited that often. It might be weekly or even up to monthly on some of these sites. So we're not going to have a lot of data on there, but it doesn't mean that they're not doing the job. That's the risk. So if we can move on, please. So from the top end of our small sites to our medium sites, we're now looking into our numeric consents. These will often have storm and emergency discharges towards the top end. They're generally more complicated. So at the bottom end, it might be multiple package plants put together. So we've got flow splits and things like that to deal with. But it could be larger filter works, oxidation processes, things like that. So a lot more complicated. Generally, these will have other complicated processes compared to our simple sites. So they're going to have mechanical screening and things like that on site. So there's a lot more to do when we're looking on site. We're going to do that basic monitoring because it's a good method of seeing where different parts of the process are doing, and we can do that through process. So if we think we've got issues, we can work back through the process, doing all of those kind of things. We're monitoring those critical parts of the system as well, just like on the basic ones, but now we're moving up a bit. We're doing a lot more monitoring. So a lot of these will fall under the MCERT flow monitoring. So now we've got some real data, some real-time data on the back end that we can interrogate. We've probably got level monitoring on storm tanks, things like that, so we can see when they are filling, when they're not. As we've already spoken about, we've got event duration monitoring. Certainly on the larger sites, they will fall under that. And we're starting to get some kinds of automation. So we might have desludging on PSTs and humus tanks, but only on a timer. Nothing exciting, but only on timer. And then we're into our OSM, as Dominic's already sort of covered, and our open wastewater treatment sampling as well, which is all done by a third party from us, even though, as Dominic said, it's the water industry, but it has to be done by a third party so that it's fair, so that we can't alter when it's sampled and things like that. So we do get a degree of scrutiny from that. The recording and monitoring of data, we've now got quite a bit more data. We've got real-time data almost on a lot of these things, so that we can interrogate them as it happens. This data is held electronically so that we can easily access it wherever we are. And during the pandemic, that has been a godsend for all of us working in process controls. It's easier to gather, it's easier to report, and we can report it fairly good. What I will say about this whole bit is it's very resource intensive. So this is where most of our manpower spend their time. This is going to be at the bottom end, definitely once a week, site visits, through to 3 times or more, possibly weekends, depending on the risk that is put against it, that we see from that. So that gives you an idea of we're getting a lot more complex now with those works. So next slide, please. So now we're on to our high risk, our larger sites. So these are the biggies from around the country. These deal with cities and things like that. So numeric consents, again, storm and emergency overflows, probably both on these, maybe multiple storms. So we've probably got settler storm and growth storm on this. These are a lot more. Complicated sites. They treat very large volumes of sewage. They've almost certainly got some kind of industrial effluent in them. So they're having to deal with probably slightly different processes. And in that, to manage these really large sites, we have to put in more automation, which is more cost. So we will use the basic observations and basic checks that we've done on all the others to check that our automated equipment is actually doing what it should be doing as a secondary check. So we're still doing that, and they're still relying on observation, but we're doing that to make sure that the data that we're getting off from our overriding information that we're getting is correct. So monitoring, yeah, we'll have flow monitoring, we'll have both probably now moving into this AMP period, inlet and outlet. We'll be level monitoring at probably several places throughout the site, because we'll have intermediate pump stations and things like that as we move through. So there's a lot more data of where these flows are going and at what times, and that gives us information on where we might have individual asset problems in between. We'll have a lot of equipment failure monitoring because there's a lot more automation, so there's a lot more things to go wrong, so we need to react to those as quickly as possible. We've got the event duration monitoring, but we've probably also got on these now, we're looking at action limit alarms. So responding, because we've got this real-time monitoring, we can respond before we get to a problem. So we will know the time to consequence. So we can go, right, we need to act at this point here to stop an issue later on, should we have some kind of failure on site. And we will have the OSM sampling, which is a lot more increased on these larger sites. There's a lot more demand for that information, and the urban wastewater as well. But now we're moving into, as we've sort of alluded to, monitoring and control. So we will be controlling through the process. So we might limit flows and control them through a process to make sure that we get the best out of that process. We might be diverting flows through to and holding them in balance tanks or holding them in the network to manage that flow through our system. One of the things that we've also got is that we can inhibit certain processes and divert into others to make sure that we get everything that the best effluent that we can in the situation. So it could be high level flows or things like that. So we have also measuring difference between different meters. So that could be level meters, that could be pressure monitors. We can monitor the difference between these two, which gives us another reading. So we've got another view of what's actually happening, not just that it's climbing, but that we've got a differential, and that then can feed into an action limit, which then gives us something to react to stop this. For these larger sites with SCADA, and because we've got a lot more automation, we can remotely control these sites. That's one of the great things about SCADA. We can, if we need to, reset the site from a central location. So we don't have to send somebody out at 3 o'clock in the morning. It might take him an hour to get there, an hour, he might be on another site dealing with another issue, and it might be half an hour before he can get off that site, then an hour to get there. So if we can put some of the, or use some of this remote control that's in there as it gets more complicated, then we can save ourselves some time. All of this automation and control allows us to treat these large, huge volumes in some respects with less manpower, but it's at a cost. It's at a financial cost of putting all this equipment in and maintaining it. But what it does do is it gives us lots of real-time data that we can use to stop issues on site. And that's where we are with that. So if we can move on, please. So in AMP7, as we've already touched on, we've got the flow to full treatment and EDM under UMON 3 and UMON 4. This gives us a great opportunity to use this information that we're putting in to link to other data sources using sort of multiple input alarms. So if we've got high levels coming in, but we're not seeing them going out, if we've got high levels coming in, but with it's not going through the right part of the process and things like that, there's a multitude there of things that we can link together to give us a real picture of what's going on. I'm going to come back to UMON, the AMP7 thing at the end with the demand for data, because there is a question over data. But New technology. So mobile communications means that we can have monitoring on sites that we didn't think was possible. I'm sort of thinking about my MOD days now, where we've got sites right in the middle of moors, 30 miles away from anything. We can now monitor that easily, cheaply, so we can get that. As technology moves on, the cost greatly reduces. The size of bits of kit, so we can put them in better places. We can swap bits of kit out for newer, more information, live information, rather than, yes, we've got a bit of kit, it goes in, but we have to go and download the data every month or whatever. We can now get that live, so that comes in. And greater functionality. We don't have to go to site. A lot of the new technology is smart technology. We don't have to go and dismantle it or plug in. We can Bluetooth to it. We can alter settings if they're wrong. We can diagnose what's wrong with stuff by Bluetooth, which is amazing, you know. So we can get a lot more functionality, a lot more bang for the buck, as Oliver said earlier, out of this stuff, but at a cost of replacement. So the challenges that we're seeing is that we've got an aging infrastructure out there. There's a lot of old kit. That gives us compatibility issues. We can't just go and pick up a new thing off the shelf because it doesn't talk in the right language. It doesn't fit with the controller. Things have moved on, digital, analog, and all that kind of stuff. So we've got compatibility issues, which might mean as things become obsolete and break, we have to spend larger amounts of money than we would have done in the past, where we could just take out a monitor and put another monitor in. With that old kit becomes reliability. If we're struggling to pay for upgrades, and we've got a number of upgrades to do, and we're struggling to upgrade the whole lot of the infrastructure, then we can get reliability issues with that old kit and finding the spares to and that's the last bit, which is cost of replacement. So cost of replacing, finding spares for existing old infrastructure kit is difficult, but also then you might have to do a larger upgrade, which is a bigger cost, and that has to be weighed against the challenges that we've got. Demand for data, as Dominic said earlier, there's a thirst for data out there, both regulatory and the public. So live data request is coming, and just wanted to sort of touch on that, which is the data for UMON 4 means that they're looking at a site being recorded every 2 minutes, which will give, for the 3,500 MCERT sites out there, about 525,600 pieces of data per year, which is massive. So we have to then pay for the upkeep of that, and that's every year. So we've got data storage issues, we've got data management issues. If you add the 42,000 monitoring sites for CSOs, we're at 1.471 billion pieces of data for all of that. So that is a massive challenge for managing that amount of data, for data quality checking, for just the storage side of this. So that is really, really massive. And the more data that we produce, the more third parties are going to want to request that data, which means that we have to go through that process a lot more. Every time data is requested, we're going to have to pull it out, we're going to have to data check it, and then we're going to have to package it up and send that out. So that's a massive challenge, I think, for the company side of things. So moving on, any questions? And I think I've done that.
Thank you
in 20
very
minutes.
much, Lee. That's brilliant. I think we'll move on and to Ian Pemberton of OFWAT to talk about outcomes, because I think these presentations naturally go in a direction, and I think if we come together at the end for a discussion, I'll just wait for the mixer to look at it. We're also having quite an interesting discussion on the chat here as well whilst you're talking, but thank you, Lee, for giving us a great overview of the challenges that the water companies face. But I'm going to move quickly on to Ian Pemberton of OFWAT to talk about storm overflows and the role of the economic regulator, because it's the job that they do is massively important, because we need to get the right outcomes for the customers. So Ian, if you'd like to take over.
Thank you, Oliver, and thank you, Lee and Dominic, for fascinating presentations. I'm Ian Pemberton. I joined OFWAT 5 years ago after 30 odd years in consulting engineering. So I bounced around, primarily an infrastructure engineer, and I am one of the deputy leads of the water engineering, science and technology function within OFWAT. I have recently handed over my role as OFWAT's lead for storm overflows in England, but I retain my role as storm overflows lead for Wales, given that they have a different legislative regime. If you could move on, please, next slide. What I really want to do, I think is really important, picking up from what Lee's just said there about the funding and the costs that are going to be associated with this. I think it's quite important to understand what OFWAT do and what we don't do before we go on to looking at this individual storm overflows problem. And I think I would be the first to admit that when I joined, I thought I knew what they did, and it's probably slightly different to what I thought after 30 years. So I'm going to presume that if I didn't understand when I joined 5 years ago, that maybe some of the people on the call don't understand either. So if I give a very quick pocket history, a pocket position of OFWAT and what our role is, and then I can come on to the function in storm overflows. Can you take the next slide, please? Forgive me for telling you things you already know. Water industry was privatised in 1989, and as part of that, the Office for Water Regulation, OFWAT, was created. And our powers and duties and responsibilities are primarily set out in the Water Industries Act 1991. There's 3 or 4 slides here that's slightly out of sync, but I'll come back to them. The water companies are obliged to maintain water supply under Section 37 and to effectually drain under Section 94 of the Water Industries Act. Next slide, please. In terms of storm overflows, this Section 94 obligation means that the company should effectually drain and effectually deal with the sewage from that. Effectual has legal connotations, but it means basically fit for purpose. It needs to do it. What is expected of it, and then you can get into case law and interpretation as to what does effectual actually mean. But I think macroscopically, taking a helicopter view, I think we know what that means. I think, and often is the case, particularly with resilience and with other things. What is wrong, what is right is determined by what is wrong, which is then determined by case law. So you have to get over the line to get something wrong to work out where the line is. So in many places, it's actually it's in the company's interest to stay well ahead of that curve. Next slide, please. Could you do a next slide as well? Then we'll go back one. There's two amendments really to that Water Industries Act. The 2014 Water Act, which imposes a resilience duty on OFWAT as well. And then also the Urban Wastewater Treatment Directives 94, which sets out again obligations of the company as to what they should be achieving. The important thing for me on this presentation is that we have responsibilities and duties to enforce these obligations. So basically, macroscopically, we're looking at wanting the companies to actually deal with wastewater, to provide a wastewater service to their customers, and to convey it and treat it effectively. Could you go back one slide, please? There we go. So these are our fundamental and primary duties. We are the customer and the consumers. I'm Diaz here. We're the economic regulator, so primarily looking at the economics of the sector. And what that means is, I guess it's good to draw an analogy with supermarkets. So with supermarkets, we have a choice whether we want to go to what would be perceived as a value provider, or whether we want what we perceive to be a quality provider. We have a choice as to whether we go to the nearest or whether we go to the largest, whether they have a range of stock, whether they go to whether they have our preferences in terms of organic or low cost, or maybe suppliers. So that's getting towards what we would call a free market economy, and those individual companies and suppliers are able to flex their market share by offering services to attract individual customers. Economists love that. Economists love a free market economy because it means that the suppliers have to provide what the customers want, and then in competition, and you get natural meeting of supply and demand. So if one company can provide it at a lower price, then customers are free to move. Water companies are regional monopolies. They don't have the ability to Oliver, would you mind going on mute, please? I think you was typing that. Yeah. Thank you. Where was I? So water companies are regional monopolies. They don't have the ability to increase their market share. They don't have the ability to move their boundaries to supply a neighbouring company. And we don't have a choice as to who provides our water and wastewater services. So the role of OFWAT is to provide quasi-market conditions. So we would expect the companies to engage with their customers, to understand what it is that their customers want, what they need, what their willingness to pay is, and then to make sure that the companies are provided with sufficient finance and sufficient tools to be able to deliver those customer expectations. And we do that through periodic price reviews, 5-year price reviews. As they just said, we currently have 7, and no doubt the companies are now starting to move their thoughts towards the PR24, the price review in 24, towards AMP8 planning. And that sets spending limits for each of the companies, but it also sets objectives and outcomes that the companies have agreed with their customers and have agreed with us that they will deliver. And there is a pain gain mechanism in there through outcome delivery incentives. So where companies can outperform and their customers want them to outperform, then they will receive more money. But the customers are prepared to pay more on their bills if the companies are delivering a greater service. And obviously the counter side of that as well. So coming back to the economics and how we price things and what we do, our role and our function is to ensure that an efficiently run company has sufficient money to deliver its services to its customers. An efficiently run company. And there are three elements to that pricing, which is a base cost. Base cost would be everything which is common to all of those companies. So whether it's the price of a ton of sodium hypochlorite, whether it's the cost of buying a transit van, whether it's the cost of a technician for a day, that base cost should be similar across the whole of the UK. And there are two, there are functions within the economic regulation which allow a company to say our particular cost of that particular component is different. If you are in the southeast of England, you can argue that labour costs are higher than they might be elsewhere. If you are a remote area, you can argue that your distance to site and therefore your transportation costs are higher. So there's a special cost line and special cost factors that the companies can bring to their price reviews. And then the final element is an element called enhancement, which is I have delivered this efficiently. I now want to, and I've agreed with my customers, I'm going to deliver an enhanced service. It will be better, and that's over and above my minimum requirement to deliver, and to therefore look for an enhancement cost and enhancement spend. And those are analysed by us on a case-by-case basis. What you come at the end of that is a pot of money, a price review. What we don't do, what we absolutely don't do, is to say for companies how they must achieve those outcomes. You must do this and you must not do that. It is for this is the whole idea of competent and efficient companies that they can actually run their businesses how they see fit towards delivering those outcomes. So if you want to light the blue touch paper and retire, say OFWAT letters, because that will really set the hairs running. That's definitely not what we do. Next slide, please. And again, thank you. Right. So coming on to overflows. That's a bit of a wicked problem, this one, isn't it? It's something that's really come to public fruition, public awareness, particularly through the Panorama programme and through government interest. Philip Dunn and its private members bill, and now Rebecca Powell, who is the Junior Minister for the Environment, pushing for action. Back in 2013, I believe it was, that the 21st Century Drainage set up targets for storm overflow monitoring, and at the moment, there is a plan to get those monitors in, which was initially going to be by 2025. It's now been accelerated as a result of the task force to 2023. And that there is a plan that the DEFRA will publish a plan on how to reduce harm from storm overflows, which is due for publication by September 2022. Our expectation and our position is that we want those solutions to be evidence-based and to be the right solutions. And that's based on other environmental goals and in the interest of customers. If you could move on to the next slide, please. And I think that there's a degree of pressure on us all to act. There's a degree of need to respond quickly. And I think from our perspective, we're looking to say, actually, we want to see storm overflows dealt with as part of a wider holistic solution. We think there's a number of root causes to the problem. Whether those overflows, sorry, I should take it back one step and say relatively few, if any, overflows have been installed since the 1960s. Since the 1960s, the companies have been designing and installing separate foul and surface water systems. So this is a legacy problem. It's back. It's come to public attention now, but it is it's openly a legacy problem. So some of the problems that we think are there, poor design. Maybe they were designed based on flows in the 1950s and 60s, and now they're in a different place. Whether the settings are correct, whether it's just a as Lee said, technology moved on, the world moved on. Maybe they're in a bad state and just badly designed. There's a certain degree of misconnection of surface water to foul sewers. And Urban Creek, I think I think we all agree is a significant contributor to the problem. Actually, customers connecting their impermeable areas to the sewers. I'll come back to sewer misuse because I think that and the right to connect, for those who don't know, and under Section 106 of the Act, any new property developer has the right to connect their property development to the wastewater network. The companies have the right to charge both an infrastructure charge, a connection charge, and a reinforcement charge. So they can charge for the unit impact of that development. To say that actually, on a per capita basis, it's going to add this to my costs, therefore that's your charge. But then they can also do to say that I cannot, the network as is cannot sustain that level of development, and for you to connect it, what I'm going to have to do is to do this level of reinforcement downstream, and that's a bit of a minefield for the developers and for the companies to actually push back. And I think my personal view is that it's too hard for the companies to refute that, and it's very, very difficult for the company to say this is the straw that breaks the donkey's back. This particular one development is the one which takes it over the edge. It's a creeping death. It's an incremental problem. Climate change is certainly an issue, that we are going to get more and more intense precipitation and intense snow melts. I think from our perspective, and I'm sure from other regulators, it's kind of, climate change is no longer an excuse. It's a fact of life. Climate change is now business as usual. It was a problem. It was something that came out of the woodwork. It was something that was left the field. It's now there. So it's sort of it's a bit overused, in my opinion, as a reason for non-performance. Yes, it is there, but it's real, and as we saw with the Section 94 obligation for the companies to come do something about that. I think the operations and maintenance is a key issue through customer misuse, operational maintenance, and infiltration. whether or not the sewers are in as good condition as they could be, whether we're actually creating a problem through suboptimal operation, maintenance, and replacement schemes, whether they are efficient, whether they're as efficient as they could be. And I think, coming back to our role as the customer's champion and our role in making sure that the customers get what they want and pay for what they want, there is some work to do around customer perceptions of misuse and fat soils and greases and the wet wipes and non-flushables. The horrible stuff that members of the public see in the water courses would put there by the institutions represented on this panel. They were put there by customers. So there is a cycle that has to be had there in that there is a degree of responsibility, and I think it's probably the next generational thing for us to look at. When my kids, if they saw a tap running, they'd go and turn it off because they've been taught to not to waste water. And me growing up, you can remember point click and put your seatbelt on, and maybe even in the 1950s and so, people might have been more cavalier about drink driving. So there are things which are going to change through generations, but there's a job of work to do for the sector to educate the public that if you stick it in the toilet, then there's a chance you'll see it in the water course, and that's become politically unacceptable. Next slide, please. So really, I think this is my last one with the questions. Our driver, our desire is to see the right solutions. I should have said that one of the other potential causes of this problem is hydraulic capacity, and whether that's capacity in the sewer network, and whether that is a problem through the misconnection, or whether that's treatment capacity is a moot point. It transpires that a lot of the overflow problem is at the water treatment works, wastewater treatment works inlets. A lot of it is being spilled on the networks, and the larger volumes and the longer duration spills are at the treatment works. So the logical solution for that, the easy solution for us all, the lazy solution to jump to is where we need to just build storage tanks at the treatment works to deal with these large influxes of flows. And that might be the right solution, but our position is we need to look at that as a holistic solution. Do we really want that heavily carbon embodied grey solution? Do we need customer-based solutions? Do we need operations and maintenance? What about blue-green infrastructure? What about separation? What about more efficient operation and maintenance of the networks? And if the right solution is grey infrastructure, then of course it's the right thing to do. But let's not just rush towards that as a solution. That needs to be supported by the customers. What do the customers want? And it needs to be affordable and financeable and deliverable. Perfect storm 2021, end of pandemic, furlough, energy crisis, global supply chain crisis. Yeah. Are we really going to, we collectively as a sector, going to recommend that this is a massive investment program that's going to happen in Rampage, and that customers are going to pay for it. Is that the solution? Yeah, really? So we definitely want to see the right solutions being achieved. We want those to be customer supportive and deliverable and affordable. And I think part of that is taking a more holistic view of how Storm Overflow integrates with other programs, and what we can do to deal with the causes of this problem rather than with managing the effects. Next slide, please. I think that's me. That's good. Well, thank you. Thank you for listening. Thank you for the panel for nodding and not looking.
Thank you. To me, that was absolutely fascinating. I love the bit of Ofwat's point of view of the problem. I think that was a really fantastic summary. And I also, the last bit on, are we really going to go into that massive investment program? I think it comes to it. I think yesterday in the Environment Audit Committee, I think one of the CEOs came up with a cost of about 200 billion to separate the sewers. To me, my rough mathematics on the number of households, that would be about £1,200 per household per year for the next 10 years. So I think that would put the average water bill up to about £1,500 a year, which I think there'd be riots in the streets. And so, yeah, no, a massive infrastructure project isn't feasible, to my mind. I'm very happy to be wrong and that to be done, but also the practical elements are there enough civil engineers in this country to deliver that? And I think you'd probably go, no. I've certainly seen from the Environment Audit Committee, looking at it yesterday, monitoring as well. We had from Dom the upstream, and Lee also said the upstream and downstream, how many overflows, how many treatment works. I make it somewhere, I've had various figures for various things, but I make 10,000 treatment works, 3,500 under inserts, which is what Lee was saying as the medium sites and above. I think Dom said 15,000 overflows. 2017, I had a figure of, I think from Phil Hume, about 17, 18,000. You were talking about 50,000 measurement points, more or less. And the cost of that absolutely staggers me as well. But maybe that's the way we need to go. We have had some questions from the panel. This one's to you, Dom. How explicit is the requirement to continually measure water quality in a river? Getting traction to supply water quality kit to water companies is still difficult.
Yeah, it's included in the bill at the moment. It was a Lord's amendment to put in upstream and downstream of all storm overflows and continuous discharges. There is something in there around it needs to be, the regulator has a say in this, and I think what we need to do is, I think the requirement will be there. It will be to go away. The public demand is for it. I think as it evolves, the practical implication of that will be the challenge, and that will be we've advocated that it needs to be done on a risk basis, and that there will be certain circumstances where it may not be possible. But I think the principle is there, but there is a caveat in the bill as written at the moment that allows for some risk-based decisions to be made around that. But it will, certainly if that part of the bill gets passed, then we will be doing it. It will be a question of outfalls, and then how long is that going to take? Because, as you say, massive. The practicalities of it, as well as having enough engineers and so on, I'm just thinking about, well, it's not as easy as just upstream and downstream of an outfall, because these are supposedly permanent structures. So you're looking at gauging station type infrastructure, with vandal proof, flood proof, and all of these things. So all of these things need to be considered. The public desire is there. Certainly the political desire. What they're seeing is it's because of the ADM data, really, that we're now seeing. People are becoming aware that storm sewage goes into rivers. There wasn't a great awareness, apart from in very small sort of communities of NGOs and so on and so forth. What it has, it's got it on the political agenda. And I think what we need to do is understand that this is coming. We will have to do it. But again, what's the pace? How we're going to do it? How do we make it risk-based? And there will be lots and lots of discussions with OFWAT and with DEFRA and the NGOs, be largely through the Storm Overflow Task Force, about how we implement that when it comes in. At this moment in time, we don't know exactly what's coming in, because it's just a bill and it's got to be passed, and there's lots of discussion to be as yet. But I can't see it not going in some form. So we have to, as a sector, be able to respond to that.
You see, myself as an environmentalist, an engineer and a scientist, I have got this duality in me. And I realise environmentally it's absolutely the right thing to do. As somebody who's got a huge amount of experience in instrument installations, 100% agree with you. It's going to be gauging structure like installations, and it's going to be incredibly costly. And then on top of that, the operation and maintenance. I did a rough calculation in my head this morning. Even if you use an ISE technology, relatively inexpensive compared to gauging structure and up and downstream, you're looking at least £1 billion. But then on top of that, you're probably looking at about 1,000 instrument technicians nationally a year, at a cost of say 100 million, and then the renewal capex cost on top of that. So yeah, I mean, the environmentalist in me says absolutely the right thing to do. There's governance issues of who should be measuring in the river. Then there's maintenance, operation and maintenance issues rightly brought up on operation and maintenance, instrumentation, absolutely. And then we're also possibly looking at, dare I say it, an MCERT style scheme for that quality assurance. And I know that's jumping ahead, but we've got to have that quality assurance, because yes, you pointed out the 400,000 overflows, and I think it's something probably to discuss in the next session. But in terms of the ENGOs, I think we've probably got a duty to give them more information about what those spills are. Are there full spills due to instrument problems? Are there spills in dry weather? Are there? And then that's bringing data sources from other areas.
That's the air war. That's the media war. It's the understanding of the need for storm overflows as it stands, or as the chief execs discussed at the task force yesterday, it is the order of £200 billion to eliminate storm overflows potentially, and part of the Environment Bill asks for a report on how you might eliminate storm overflows and what the costs would be, and so on. I think it says within a year produce a report, and I think we've all come up with figures I think that 200 billion is similar to figures we came up with through the Storm Overflow Task Force. I think was more than that, but it was the order. So we've got a good idea already. We're being asked to produce a report on that, and then that will inform the political thinking there. But I think a big part of it is that understanding of the the need for storms. What's the difference between a compliance bill and a non-compliance bill, as you say? But the public don't care. They just see storm sewage, and it's always raw sewage in the media. It's never storm sewage going into the environment, and that's I think is when this information starts to come through and required by the Environment Bill and such like. Before that does, we've actually got to get that media war right, their war right with the customer base, so they truly understand. Going back to what Ian was saying, I think we're very much for sustainable solutions to these storm overflow issues. We don't want to pump and treat surface water. We want to get the surface water out the sewers, and through suds and so on. I think the critical element there is the demand. Well, we will be challenged by NGOs and pressure groups in particular, who have got the ear of politicians to get to solutions quickly, and I don't want to see the pressure for quick solutions driving the wrong solutions.
Yeah, I'd agree.
We've got to work together on that.
To me, on the monitoring thing, that's especially important, because we can very easily run into the wrong solution, and that's. But equally, I think some of it is probably, if we say £200 billion to a customer, that's monopoly money and doesn't mean anything. If we say it's going to be over the next 10 years, it's going to be 1,200 quid on your water bill, that's going to mean a lot to a customer, which is really important. And I think the other challenge, I think it's probably where you can come in, Lee, and is open data, 100% right, brilliant, fantastic. But how do we present that? Because I think, Lee, you talked about 1.7 billion. Depending on what data actually goes out, that can be into tens of billions of pieces of data, which is useless. It's great for the data scientists out there who want to play with the data, fantastic. But what does the customer want to see? How can the stakeholder consume that information, or do they want the raw data? Some will want raw, some will want,
Yeah, I think there's like Dominic sort of touched on there, there's an education piece there, because you can give them all this information, but if they don't know what they're looking at, they can get it and they can make whatever conclusions they want, exactly like every storm overflow, if it's discharging, is non-compliant and it's raw sewage, and oh my God, it's the worst thing in the world. But it's not always like that. It's a compliant storm overflow 6 times, dry weather flow, all that kind of stuff. So there's an education piece that goes with it, and it probably links on to the education about what people are putting into the sewer as a whole piece, probably for all three of us here groups. The water industry, the Environment Agency, and OFWAT, educating as a whole as to this is what it means, and that bit there comes out with then showing them the data that they need, that they want to see, but in a way that is clear and shows the correct messages.
Well, one of the things that came out of the Environment Audit Committee yesterday, and I picked up on, was a more recent figure for the cost of blockages, and I think that was 200 million, if I remember correctly. And that's, again, that could be a piece. Well, that's everyone. That's costing you £10 a year.
Yeah.
quite simply, is that case going? Again, Ian mentioned the education piece with his kids. One of the things we're talking about later in the round table is net zero, and we've got a great example of water stewardship from Denmark. That piece that Ian was saying, kids are being taught, that was done a generation ago in Denmark. So is it a cultural and generational thing? Possibly. I remember when I worked for Yorkshire Water, seeing little 4 or 5 year old kids being taken around Esholt, and it was the most wonderful thing to see. I think some of the water companies are doing a massively brilliant educational piece. I love the stuff that Severn Trent Water did over the pandemic of doing virtual wastewater classes. So again, there may be a generational thing. And again, we'll talk about it this afternoon with net zero, the potential of serious gaming as well. Anyway, I think we've run out of this time for this session. I'm sure the questions could go on for absolutely ages. So thank you, Dom. Thank you, Lee. Thank you, Ian, for a fantastic introduction to the Flow Forum. It's been really, really valuable. We're going to take a comfort break now for 15 minutes. Do come back at 11:15, where we've got Jacqueline Diaz Nieto from Yorkshire Water, Rob Stevens from RS Hydro, and Christine Colvin from the Rivers Trust, all talking about how we measure, how we can communicate with the customers. So thank you very much for the first session, and see you all in 15 minutes.
Thanks, everybody.
Cheers.
Thanks, everyone. On to our second session of how we measure. We're going to hear from 3 fantastic speakers on how we're going to measure the wastewater system, how we're going to measure pollutions to the environment, how we can measure pollution in real time, and how we can most importantly visualize it. I think one of the things we talked about in the last session was visualization being really, really important. How we can give that to our customers, the industry's customers. And Christine Colvin at the end is going to show us and visualizing the state of our rivers and CSOs. So it's really, really important. So without further ado, apologise for being a couple of minutes late. I'm going to introduce you to Jacqueline Diaz Nieto of Yorkshire Water, who's going to talk about monitoring the wastewater network. Jacqueline, do you want to take it away?
Okay, thank you very much, Oliver. Yeah, thank you again. I'm Jacqueline Diaz Nieto, Wastewater Network Strategy Lead at Yorkshire Water. And thank you very much again, Oliver, for inviting me to speak at this session on behalf of Yorkshire Water. A lot of what I'll be taking you through today is the end product of a number of teams working together, including operations, control room colleagues, OT, IT, data science, asset management, innovation, dynamic maintenance, and our strategic planning partners, and probably many other teams that I've missed out. So it really illustrates the multidisciplinary nature of digitisation and this journey that we're on. So we're working on developing Yorkshire Water's smart wastewater network strategy. And today what I'll do is I'll take you through some of the journey and learning so far. The backbone of the smart wastewater network journey, of course, starts with the monitoring, because as the well-known saying goes, which has been said several times already this conference, you can't manage what you don't measure. So as part of this journey, one of the first steps was to establish a baseline in terms of what we already measure and monitor on the network, on the wastewater network. And last year, as I was on the start of my part of this journey, I heard a quote which sort of got me thinking at another conference, an urban drainage group conference, which struck a chord and sort of set me on a path, really. Because I think it's of great relevance with regards to monitoring and the process of transitioning to a smart wastewater network. And if you click now, please. It was the Donald Rumsfeld quote which got me thinking, you know, there are the known knowns, the things we know that we know. There's the known unknowns, so we're aware of things that we don't know. And there's the unknown unknowns, so most of us will acknowledge that there are things we don't know that we know about. But the bit that I found particularly interesting when I heard it, and sort of the sort of new spin on the quote, the fourth category, which was a water industry colleague sort of brought it to light, was the unknown knowns. So if you click again, that's please. Yeah, so the things that we know we have, but we rarely look at. And I thought that got me thinking, especially in current times when there's a requirement for all storm overflows to have event duration monitoring, the EDM, and many of the network pumping stations and a lot of our network storage assets are already fitted with level monitoring and flow monitoring equipment. So there really is a wealth of information that's being monitored and measured on the wastewater network. And whilst the assets have alarm points, they, as an industry, I believe we could do a lot more to look at the data in real time and from a holistic and operational and systems-based approach. So we all know this is very much in the course of changing as technology and artificial intelligence penetrate all aspects of our business. Then I'm sure sort of my previous statement is there's a lot of work already going on in that area in terms of exploiting the data that we already monitor on the wastewater network. So given this session is about monitoring the wastewater network and how we measure, what I'm going to take you through next is some of the more recent monitoring initiatives, additional monitoring initiatives implemented on the wastewater network at Yorkshire Water, and share some of our experience to date, as well as some of the key learning points and benefits observed. So if we go click now, next slide, please. So just leave it there for now, yeah. So in AMP6, Yorkshire Water implemented a number of upper quartile initiatives to address pollution and sewer flooding drivers, and a lot of it was around additional monitoring to get additional insights. So we installed 1,000 level monitors in sewers. We also installed over 1,000 monitors at properties at risk of internal sewer flooding due to other causes. So they're the blockages when we refer to other causes, blockages and structural failures. And also pressure monitoring was installed at 60 high-risk rising mains for burst detection. And this AMP, in AMP7, feeding off the learning from that first iteration of property gully monitoring and taking an improved approach, we installed a further 500 monitors on properties at risk of internal sewer flooding due to other causes. We've also evolved how we use the sewer level monitoring, this AMP, by applying artificial intelligence and bringing in the rainfall data for better blockage detection. So that's using the EDM from the CSOs and the level monitoring that we put in AMP6 on the main sewers. We've learnt a huge amount about how to interpret the rising main pressure data and detect failures. And now we're at the point where we're using sophisticated logic to configure alarms for rising main burst detection using this data. So some of the learning is actually feeding into the logic behind our alarm systems for the rising mains. So what's the challenge? I mean, most of us present at this conference session will be all too familiar with the challenges associated with pollution and flooding from the sewer network. A particular challenge for Yorkshire Water, and hence why we've focused quite a bit on the internal sewer flooding problem, is that within the industry, and we set out to address this with increased monitoring, is the internal sewer flooding challenge. So Yorkshire Water has one of the, in our region, we have one of the highest numbers of cellared properties in the country, and these account for a large proportion of our internal sewer flooding incidents. And the question we set to address was, how do we get greater visibility and early warning of the blockage formation on these small diameter lateral sewers, of which there are a high number of them. So it's related to the unflushables issues really that are leading to much of the internal sewer flooding observed in Yorkshire. So we wanted to draw on some of the learning from the clean water distribution network with the leakage drivers and the way that they've used monitoring for leakage, but we acknowledge, or we sort of learnt along the way, the unique set of challenges that are faced with the wastewater network. In terms of a starting point, the wastewater network is less monitored as a baseline, and the key thing is service failures tend to come to light. We tend to discover them all at the same time, which is when it's during wet weather, when it's raining. So there was a real risk that greater visibility through more monitoring would actually create more work in a concentrated space of time, as in when it's raining. And thirdly, the nature of the fluid and the aggressive environments which the monitor equipment has to endure is very different to the clean water networks. So the next few bullet points which my colleague will go through slowly on this slide. I'll let you know when to click. The first, I'll give you an overview of the how we measure and monitor CSOs with EDM, which was the first bullet point. But I won't go into too much detail, as EDM is generally well understood, and there's industry best practices that we can refer to, such as the WWEM Urban Drainage Group Good Practice Guide. A lot of the recent excitement, however, and quite rightly, is how water companies can use that existing and regulatory required monitoring to derive additional benefits and insights, and the application of AI and machine learning to EDM data for blockage detection is becoming more common and widespread to prevent discharges in dry weather. And we at Yorkshire Water have applied AI coupled with rainfall data for improved blockage detection at over 50 CSOs with EDM throughout the Yorkshire Water region. We've seen the benefits and improved insights that applying the AI compared to a pollution predictor, which we've used for several years now. It's we've seen the benefits of applying more sophisticated AI compared to the pollution predictor that had served us really well for a number of years in terms of detecting trend changes at CSOs. What we found is that with the AI and the models built for the CSOs, colleagues in the control room have much greater confidence in raising work for the field colleagues to investigate anomalies spotted via the CSOs that have the AI models and the AI tool applied to them. In addition to the AI models, we've applied this AMP. We've got a proof of concept project where we've also started monitoring our CSO outputs using CCTV. So that's the CSOs and EDM in terms of what we're monitoring and measuring and where we're going with them. So the next one is the sewer monitoring. So if you click now. In AMP6, we used some spatial analytics and historic pollution incident data to identify and prioritise 1,000 locations on the sewer network that would benefit from sewer level monitoring to prevent pollution incidents by having an early warning of blockage formation. These 1,000 locations, initially fed into the same process used for the blockage detection at our CSOs, which was the what we referred to as a pollution predictor. But some are now benefiting from AI models as well, which obviously have the increased predictive power of the rainfall and a specific model being developed for them. The next one, next click, please, is the property gully monitoring. In many ways, the principle for monitoring the wastewater network to detect blockages on lateral sewers is no different to the main sewer level monitoring. In effect, what we want to do is learn what the normal behaviour looks like and then be able to detect any deviations from normal behaviour, both in wet weather and dry weather. However, the challenges associated with the gully monitoring, or the property level monitoring, and some of the key learning points from our first iteration in AMP6 were around the size of the devices. So clearly the size of the conventional sewer level monitoring equipment was not appropriate for the gully locations. There were programme challenges associated with the large numbers of sensor deployment required at property level, gaining access to private property, introduced programme timescale risks, and interestingly, customer behaviour, very curious around the devices and in some cases interfering with them. And just, I mean, it's an obvious one really in hindsight, but the large volumes of data generated from all these devices and learning to interpret that data and having that confidence of when interventions are required. And we learned a lot about the data visualization challenges for our colleagues in the control room that had to sort of take action off the back of the data. And it's also fair to say that from our field colleagues, initially we had some challenges regarding responding to some of the alerts from the first iteration of the devices, sort of leading to a lack of confidence in the data as we were learning to interpret it. So we learned a lot from the first deployment of property gully sensors. And in AMP7, we deployed a further 500 property gully monitors. And some of the things we did differently were that we took a different approach to gain access to properties to ensure that the programme timescales were met. We improved the data visualisation and analytics for control room colleagues to act on incoming data. We've also learned a lot about the typical blockage formation, so the feedback from the field has been really useful in identifying typical lead times when we spot an anomaly, so that jobs could be raised on right timescales, so there wasn't a need to sort of react with a high priority for all of these spotted anomalies. And again, this has helped a lot with increasing the confidence of the field colleagues to respond as required. And we're evolving our specifications for the type of monitoring equipment required at property level on the lateral sewers, in terms of the methods of installation, the parameters that we monitor, and the type and size of the devices and the telecommunications used. So the next and final aspect of sewer monitoring, wastewater network monitoring that I'll talk about is the pressure monitoring of rising mains for burst detection. So one of the main challenges, and I think there's a talk later on in this session as well, which will be really interesting, is with regards to the pollution incidents from the rising mains from pump systems. The very nature of rising mains means that they often go through rural locations and they're pumping across catchments. So they're prime candidates, these rising mains, for crossing paths with a water course and causing pollution if they happen to burst near the water course. And the fact that rising mains often pump across natural drainage catchments through sparsely populated areas also means that bursts often go unreported for long periods, which obviously increases the impact of a pollution incident. So anything we could do to mitigate that, identify that burst earlier and mitigate the impact was a benefit. So in AMP6, we identified our critical rising mains in terms of pollution risk and prioritised them based on the risk of failure, which was generally associated with the age of main, and we found in the pipe material. And we installed pressure monitoring on 60 of the high priority rising mains, and a business process was put in place for a dedicated control room colleagues to monitor the data and raise work for field colleagues where anomalies were identified. So again, we've learned a lot about how to interpret the pressure data internally. Our own colleagues have become have developed expertise in this, and we've evolved this initiative to set dedicated rising main burst alarms, as I said at the beginning, based on logic. So rather than colleagues scrolling through the data, it's now being more automated and feeding directly into our alarm system. So in terms of concluding, I'm not sure if there's another bullet point now, but in terms of wrapping up, in terms of the future and where we're going next, we've got a number of innovation projects looking to take our smart wastewater network approach to the next level. We're looking into the potential for using real-time control to reduce intermittent discharges with all the data that we've got coming in from the network, understanding the levels around the catchments. We're investigating how smart water meter, so from the distribution side, linking up with our colleagues there, how that data could be coupled with sewer performance monitoring. And the question or the hypothesis we're asking is, can that generate greater insights into the system behaviour, as well as we're continuing to evolve our monitoring capabilities at the property level to address the internal sewer flooding driver. So I hope that's given you an overview of how we monitor the wastewater network at Yorkshire Water. And just to return to the original quote from Donald Rumsfeld that I mentioned right at the start, I think we've come a long way and learned a lot, and are continuing to learn about what having network visibility really means on the wastewater network, and how we use that greater visibility to implement a smart wastewater network. So I think we now have a large number of eyes on the network and are generating and collating a huge amount of data about our network in real time. However, it's very much still compartmentalised according to specific drivers such as pollution or internal sewer flooding. So a lot of the initiatives that I mentioned, they're not quite joined up yet to get those joined up insights. So I think the future challenges are about breaking down these data silos and working out how we derive the additional benefits and greater value from a holistic approach. So bringing all the parts of the puzzle, all the monitoring on the wastewater network into one place for improved decision making at a catchment systems level. And a key next step for us is about widening the application and exploiting the capability of AI and ML, machine learning, with the data that we already collect to drive that targeted investment, get to the root cause, as was mentioned in the earlier session, as well as driving those operational efficiencies. So I hope, thank you very much for listening. I hope I've left some time for questions and discussions. Thank you. Thank you very much, Jacqueline. We'll probably gather together for questions right at the end, so and have a bit more of a question centre. I know, to be honest, typically the wastewater network hasn't been monitored very well, and I think the key thing for me was the ministerial direction on EDMs was a key step and enabled the water companies to put EDMs in. And realistically, I think sewer monitoring, the sewer network monitoring, is going to take a massive step on from there. For those of you who are interested in the pressure monitoring, I've actually put a YouTube video that was done on the WIPAC YouTube channel. So after the session, after today, please feel free to go there and have a look at a nice case study that was done, funnily enough, with Anglian Water. At that, I think we'll move straight on to our next speaker, who's Rob Stevens of Proteus. Rob and I have known each other for a very long time, and is a regular at WWEM. Rob, if you want to take it away and talk to us about real-time pollution monitoring.
Thanks very much, Oliver. Pleasure to be here. Hopefully you'll enjoy this presentation. There's quite a few slides to get through. Obviously, it's very topical at the moment, and probably going to get even more so over the next couple of years. Next slide, please. So by way of an introduction, I'm just going to give you a bit of an overview of Proteus and who we are. Next slide, please. Okay. Proteus Instruments is really a company formed out of innovation. We were originally funded from a knowledge transfer partnership, which is basically a university, Innovate UK, and a commercial organisation. End product is just to try and create jobs. And it's worked incredibly well on this particular project. And by 2018, we actually launched the company at IFAT in Munich. During that time, we've scientifically proven that we can measure BOD, COD, and these parameters, including coliform, in real time. And we do it using fluorescence. But there's an awful lot of work, and there are basically 3 scientific papers behind all of this to prove our point, because we knew that the first question we will get asked is, how do you do it? And how can you all of a sudden you manage BOD? So that's what we did. We subsequently patented it. Oh, we've moved on. And in effect, it's becoming very much a disruptive technology, and you'll see this as the slides go on. And more recently, we've just literally about 2 weeks ago, we won the Institute of Water Innovation Award. Next slide, please. Okay, so in 2019, many of you may be aware that the World Bank produced a report called The Invisible Crisis. Next slide, please. And it's very fitting. And although we're not here really to talk about the world situation, in the UK, the Rivers Trust have also, as probably a couple of weeks ago actually, also released a report called The State of Our Rivers. And I won't steal the thunder that's going to be coming in the next presentation, but there's a lot. It's just to really set the scene. I mean, there are 2 main issues of pollution in our rivers, and the first of which is agriculture. And 62% of all rivers are affected by agricultural pollution in some form or other. For the water industry, it applies to 53% of our rivers, and it's mainly from sewage. But the really important thing here is that what we got to remember is that it only takes one pollution event potentially to ecologically strip a section of a river or a whole river, and it might take years to recover. The problem is that the next event is just sitting around the corner waiting to happen, and hence the problem becomes compounded. And we've all heard about diversity recently in the news, we get all those associated problems. But if you can also stop this organic pollution, then you will also be able to drastically reduce other associated pollution, such as microplastics and PFAS. Next slide, please. Okay. Some of you may be aware of these platforms. They're just screen dumps, really. On the left, we have the Surface Against Sewage app. Very good. It's all based on EDMs. In the middle, we have a map from the Rivers Trust. I personally use that an awful lot. I think it's fantastic. And on the right, we have the Environment Agency Water Data Archive. They produce a lot of data, but in effect, it all comes down to event duration monitoring and a limited amount of water quality monitoring by the Environment Agency. Next slide, please. We also have bathing waters, and apart from our coastal areas, there's lots of applications currently happening for inland coastal bathing waters. But the problem is, even the one that we do have is regularly being polluted, and we only know so really because of EDM data or spot sample data. So what's the real picture? You know, people need to know what the river quality is, what our bathing water quality is in real time to be able to make a decision as to whether to use it or not. And really that bathing waters are very good, but a river has to be treated holistically. There's no point protecting just one small section because the problems, chances are, they actually originate outside that area. So we need nature-based solutions upstream and widespread engagement from everybody. And probably slightly controversial, mainly through my own experience, because we have the technology. I would say that rivers are far more polluted than we think. Our understanding is based on infrequent sampling and a lack of meaningful data. The picture can only be worse due to our inability to only be able to capture the bad data. Okay, so because we can't capture that bad data, we don't really know what the picture is. Next slide, please. So how do we currently measure water quality? I mean, there's all sorts of approaches with analyzers. We have sondes, we have citizen science. I mean, we're indebted to the probably thousands of people out there taking samples and caring about their environment. We have manual samples that go to laboratory. We have the Environment Agency archive. I would point out there's very little agricultural monitoring, and that the coliform data is taken infrequently. Yeah, it's the de facto standard for understanding the quality of our rivers and bathing waters. So, I mean, the end result is that it's really difficult to identify pollution, both in time and space, and without doing major investigations, which is what the Environment Agency have to do. But this costs them a lot of money they don't have, okay, and hence they don't happen very often. And so what we really need is defensible data. The current situation is not scalable due to the lack of, to the level of maintenance and cost and resources that is needed. So it does need very much a radical approach. And really to sort of just to say that the rest of this presentation is not so much about how to provide meaningful data, but it's just to show you what has been done worldwide and shows you how easily it can be done in the UK. Next slide, please. Okay, right, so this is just a little bit about Proteus. Next slide, please. Okay, so how do we do it differently? We use fluorescence, and this is just an optical matrix using a fluorescence sensor. The one probably everyone will probably understand is if they've ever taken a gin and tonic or had a gin and tonic in a nightclub back in the day, you will notice that the gin and tonic glows blue, and that's the quinine sulfate in the drink, and that's basically fluorescence. We're using the same principle here, except we're targeting the free amino acids and proteins which abound in the microbial cells. There is obviously peak C as well, which is the carbon element, which we can also measure, which relates to TOC and DOC. Next slide, please. Okay, so as I mentioned earlier, the first thing that people will ask is, how on earth did you manage to do it? And we don't want to have to do trials with every single client worldwide to prove the point. So we thought the best way to do this, and we started this back in 2015, is to write scientific papers. And we've done that. And that proves, that's all the evidence base. So that's all out there, proving that we can do what we say we can. Next slide, please. Okay. Now, what follows next is just a series of case studies, really to put things into perspective and from around the world, and to show what can be done. Next slide, please. So this is a bit of a starter for 10. This sort of, I think for many, the penny will drop in this next couple of slides. It demonstrates that what we currently do in terms of water quality measurement, but it will also suggest the scale of pollution that is likely to exist. And in this particular example, it resolves a pollution which the Environment Agency have informed me probably lasted at least 15 years. Next slide, please. So this is a typical water quality trend. It's got all the parameters. You probably don't need to specifically know which one's which, but you've got pH, conductivity, turbidity, ammonia, and I think temperature on there as well. And if I was to tell you that there were 3 pollution events in this one slide, there's probably not anybody who will be able to point out where they are. And that is the problem. We have archives of data which need interpretation, and you probably won't get it right. Okay, so next slide, please. If you now add BOD, you can clearly see the pollution events, and then you can start looking at the other parameters and say, yeah, okay, yeah, I can see how that possibly relates. Okay, but these are very definitive events. And if you notice the timing of the events, it's the same time every day. Okay, yet they don't have a major impact on traditional water quality parameters. And this is the situation that we've got up and down the country with standard water quality instruments. Okay, you will see there's a slight uptick in along the bottom of the graph, which is a green line. It's a bit blocky, but that's because it's quite low level. It's for ammonia, so there's a slight uptick in that. But the actual situation with this was actually a farmer. Okay, next slide, please. Okay, there's a picture of a catchment there. It's roughly in the middle of England. And we basically, this catchment, not very big, probably about a radius of 5 or 6 miles. It has only 1 dairy farm in it and 1 small treatment works. We installed a Proteus within 10 minutes. And we basically were able to detect what was not detectable. So because of this pollution, this river is technically biologically dead. I've never seen a living thing in it. Okay, if you now just click the video on the top. Okay, that should play. Okay, and this is basically, you can see the color of the water. That would just never have been picked up. And the enforcement officer that came out just couldn't understand how we managed to detect it. And basically, this water was released into a land drain from a slurry tank at the same time every night for 3 nights. Okay, and there you go. The rivers just don't recover from regular events like this. Next slide, please. A little bit larger project. We have Proteus units all the way from Tibet down to Bangladesh in India. And I think the Ganges is regarded as probably one of the most polluted rivers in the world. And this is the first steps in trying to clean all of that up. It met BOD, COD, and a lot of other parameters. It's all on a real-time platform for the Indian government. Next slide, please. H2 Now Chicago, this is probably the first platform in the US to do this. And this really is a template, really, that could be used anywhere. If anyone's been to Chicago, it's quite an interesting story. Part of the river had to be reversed because it was polluting Lake Michigan. There are 3 main legs to the rivers, and there's 3 different Proteus units in there. And the end result is that they've created an app, real-time data, so that people can actually monitor the water quality and decide whether they want to use it. Next slide, please. And if it will take a second to catch up, but when it does, if you can click play. Not having it. That's a YouTube video. No. Okay. Well, it's quite interesting. It was actually on ABC News. It was a 2-minute presentation, and it just showed the news presenter actually just showed how the app worked and basically the difference it made to the local population. Okay, we'll skip that. We've been working with Philip Dunn for quite a while. We deployed a Proteus in his local constituency, just a couple of miles downstream of a treatment works, which is also to be a proposed bathing water. In the 5 weeks that it was deployed, we found 8 pollution events. And it was actually the Environment Agency that actually asked us to report it to them, which was quite an interesting situation. I'm not privy to what happened after that, but in effect, a seemingly beautiful and unpolluted river was polluted 8 times, and in one occasion quite seriously. But it was quite interesting yesterday with the Environment Audit Committee at one point where the water companies were obviously looking for technology, and I think Philip Dunn was really letting people know that the technology is out there. It just needs to be adopted and, through the innovation channels. Next slide, please. So this is for a UK water company. This is for bathing waters or coastal bathing waters. Slightly different approach. Currently, obviously, samples get taken to a laboratory, get a reading, and at some point or other, then that people get updated as to whether the water quality is any good or not. All takes time, money, but what we've been doing with one water company is actually to use a Proteus to actually measure in situ what the water quality is, and the benefits are massive. Firstly, it reduces cost and time, so you can have instantaneous results. You can declare whether a beach is clean straight away. Okay, you don't need to send the samples off to the laboratory. Okay, you can even then potentially hook this up to real-time monitoring. You could put a QR code on a beach to let people scan it and to get live readings. There's all sorts of potentials there, and you can share the data via an API. Ultimately, there's an awful lot less carbon used as well in the whole process. There is just a couple of pictures. One's a correlation of the data of all the lab readings, and there's a picture of Hannah using it in situ. Next slide, please. This is a little bit different. We got in touch with Christine, who's going to present after this, and in the lead up to the release of the State of the Rivers report, they did a stand-up paddleboard event, which started in Bristol and ended up in London. I can't say we did the whole lot. We had a few technical issues with trying to get that boat through hundreds of locks, so we sort of changed route, but nonetheless it was very, very interesting. So on that boat, you can see there is a telemetry unit in the back. It's got a solar panel, just keep it charged up because it was over a couple of weeks, and there is a Proteus mounted on the side of it. Next slide, please. The data was fascinating. So it was uploaded every 15 minutes. It's 5-minute readings, and you can see a large section of the River Thames there. Each one of those grey dots is a set of readings to every 5 minutes, and this is part of the data set. And what's really fascinating is that you can see what's happened. So that whole section was done over a couple of days. So every time it went past a significant point source, okay, they could be good or they could be bad, it would pick it up, and you can see how many events we found. Okay, what was quite interesting, more so, was that you can see in the middle of Reading there, the River Kennet comes in from the south, and the red ring at the top and bottom, that's actually, you can see the dilution effect of a cleaner river coming into the Thames. But unfortunately, about a few miles downstream, the readings went back up again, and that was actually caused by a treatment works. Okay, and there are lots of other events which haven't been investigated to date, but it shows you what is possible, and very quickly you could identify what sources are. Next slide, please. We're doing another one on Tuesday next week. It's going to be about 40 miles of the River Wye, which has had a lot of publicity, and we're going to do exactly the same thing there. And hopefully it will help us to identify the sources going along the river. And there will be a link on our website, the link's there, but you'll be able to tune in and watch as it happens. I think that's a lot. Thanks very much. I can't hear you, Oliver.
That's because I muted myself. So thank you very much, Rob. I think it's fascinating to see what we can do and what's the potential of what we can do. I mean, yes, Proteus, I love it as a replacement for BOD. Personally, you know my thoughts on BOD. I think it's a parameter that we should no longer use, and we should use something like tryptophan-like fluorescence as a replacement. It's going to take a bit of work to prove it, and I know a lot of that work has already been done by Proteus. I followed it in quite some detail for the past few years. But I think that's a discussion for a little bit later. At this, I'm going to introduce Christine Colvin. We've all seen the CSO map that the Rivers Trust produced, and it's a wonderful piece of work that helps the public understand. The public and the ENGOs, the environmental NGOs, are so important in the battle against pollution, and it is something that we've got to work in a lot closer collaboration. And yes, I think the water company is the first one to admit they've got to be held to account. And I think the ENGOs are in a perfect place to do that. So I'm going to let Christine Colvin take over and talk to us about what the work the Rivers Trust are doing.
Thank you. Thanks. If we can go on to the next slide, please. Great. So, yes, I'm from the Rivers Trust, and Rob's already given a little taste of some of the work that we're involved in. But basically, we represent a movement of local NGOs. There are more than 63 around England, Wales, Northern Ireland, and Ireland that are looking after the health of their local rivers and catchments. So we're involved around the country, working in many cases with farmers, with water companies, with local communities, involved in monitoring the health of rivers, but also in implementing a lot of the solutions in them up. So, you know, in our ideal world, this is what we'd love our rivers to look like, absolutely thriving with wildlife at the center of our nature recovery networks and being used by lots of different people for lots of different recreational activities. But of course, that's not where we are at the moment. Next slide, please. So I think these clippings were taken just from, if not the last week, maybe just the last 2 weeks. And we know that generally, you know, rivers are in the headlines for all of the wrong reasons. And the headline on the left there, you know, around the call, this is from the water sector itself, calling for a new deal to avert the crisis that we're currently facing in rivers. There's been a huge increase in public interest, I think in particular during and after COVID and lockdown, where rivers and river environments provided critical places for people to walk and enjoy and exercise. And of course, we've seen a massive explosion in open water swimming during the pandemic when the gyms were closed as well. And I think that that's going to persist because that's built up a big kind of culture and acceptance. And there's a huge desire to continue that. But massive concerns about the current health of our rivers and what's going on, what's happening in particular with the water companies and why government isn't adequately enforcing the laws that we already have. Next slide, please. So Rob already showed you the map that we first produced for 2019 data, and then that was updated this year at the end of March, as soon as the new data was made available from the water companies to the Environment Agency. So this represents self-reported data from the water companies to the EA that we have simply taken and made much more accessible. And I think, most of what I'm going to be talking about today is about, it's not just how we measure, but it's also who measures and how the data that we produce through that measurement is then available to a much broader audience in a way that is useful and relevant to them. And this CSO map highlighted one particular problem around our rivers and gives really useful information, but it doesn't give the broader context. And so, in the interest of having a really well-informed public debate around the health of our rivers and what we all need to do to help to fix them up, we decided to produce the State of Our Rivers report. Thank you. Next slide. And that came out just over 2 weeks ago. That's also on our website and covers a much, much broader range of issues. It centers a lot on, again, the Environment Agency's data. Next slide, please. Which shows, and this shows the ecological health of our rivers around the country. But where we think we've really added value here is that anyone who's looking in the State of Our Rivers report can drill in and find out what's going on their local river. And we really try and explain the data itself, how it's collated, how do we get to this final view of ecological health, chemical health, and overall health of our rivers. And whilst we try and synthesize the key information into highlighting the critical issues, we also try and bring that explanation of the analysis that's behind it so that it really helps anybody who's interested in the health of their rivers and potentially getting involved in improving them to understand the issues that sit behind this. So dotted throughout the report, we've got a lot of these nerd buttons, which you can click on, and that then takes you to another level of that would probably be more appropriate for this audience. But we know that, often the general public kind of want to skip through to the big issues and the kind of crux of the matter. Next slide, please. So we do summarize, what is deemed by the EA to sit behind the reasons for our failing rivers. The way that we've presented this data has been quite contentious because we've looked at the reasons for not achieving good, the RNAGs, or the reasons for failure, in terms of the percentage of the total number of rivers that they affect. So there's a bit of confusion when you see there that agriculture and rural land management affects 62% of our rivers and is a reason for failure on 62% of our rivers. Water industry, 53%, and urban and transport, the next big kind of sector, 20 to 30%. Obviously, those don't add up to 100%. And of course, that's because each river can be impacted by many different sectors and different activities. So this is also in the State of the Rivers report, and we unpack those key activities. the Environment Agency released the latest RNAGs just after we had published the State of Our Rivers report, but we have gone back in and updated with these latest 2020 figures. So the numbers that are reflected here are showing the percentage of our rivers impacted and failing good ecological health because of these different reasons. So we're seeing treated sewage effluent discharge is causing 43% of our rivers to fail good ecological health, and untreated discharge from CSOs causing failure in 12%. Thank you. Next slide, please. And just one more click. Thanks. So if one digs into the CSO map, there's a lot of detail in there, and you can find out exactly how many times any particular CSO overflowed in 2020 and for how many hours. This is a retrospective, so it helps to inform the public and gives you a picture of what has happened. It's not as good if you want to decide, well, I want to go down there today, what's happening today. That's where we need much more of this EDM data to come to light and to be accessible to the public. But a critical point that we try and make in the State of Our Rivers report, and this is a fabulous, it's actually a dynamic graphic, so if you see it in the report, you'll see that line moving. This came from the Met Office, from Neil Kay at the Met Office. And the grade in area is our kind of old normal. That's where our typical annual average temperatures and annual average rainfall occurred up until the beginning of this century. And where the line is starting to kind of straggle off to the top right-hand corner is actually, some of our more updated annual average temperatures and rainfalls that shows how our design envelope for our sewer system in particular is going to come under increasing pressure with climate change, which will increase our average annual temperature as well as the intensity of individual events. And essentially what we have at the moment is not going to be fit for future purpose. It's already under strain and it's already failing at thousands of points around the country. Next slide, please. But we don't only focus on the problems, we also want to talk about the solutions. And being an environmental NGO, we really highlight the potential role for nature-based solutions to help to build resilience and buffering capacity around the conventional engineered solutions that we already have in place. And I think around the world, we're seeing a huge call, from the US, Australia, China, with their sponge cities as well, looking at how do we start retrofitting our grey infrastructure with green infrastructure that's going to give us more of that coping capacity for our new climate extremes. Thanks. Next slide. And another thing that we focus on, one of the specific nature-based solutions that's particularly important in terms of sewers and sewage overspill is natural flood management, much of which is happening in the upper catchments, but also can be incorporated alongside with sustainable urban drainage in the middle and lower catchments in places where it can really have an impact. So there's a link to a dashboard there that shows where individual NFM or natural flood management sites have already been established, more than 4,000 around the country. The different types of interventions are listed on there, and the different storage as well, which at the moment is quite small. Next slide, please. And of course, the big solutions that are already in play with the two biggest impacting sectors, agriculture through countryside stewardship schemes, that's not shown on this map, but that's on another map, shows where those are happening and where they're being implemented. And this map shows a drill in to the specifics of the WINEP schemes being invested in by the water companies, what they're doing and where, and how this can also contribute to a longer term solution. Next slide, please. But of course, so much of this data that we're using is reliant on self-reporting from the water companies. Sorry, you could go back, thanks. Self-reporting from the water companies to the Environment Agency with a very little ability to then verify a lot of that information that's come in, and very little kind of independence in that value chain of data generation. And when we launched our State of the Rivers report, we had a really great panel discussion around that launch with Minister Powell and the new Director of Water Resources, John Leyland, in the Environment Agency. And we also had the investigative journalist Joe Crowley on the panel, who said, you know, for how long do we have to rely on the water industry marking its own homework and then handing that in to the Environment Agency? And that's the data that we're presenting and using. So obviously we would like to see much more independently verified and collected data coming in to triangulate a better informed picture of what's really going on. And I think that the case studies that Rob showed earlier really help to demonstrate, you know, how we've got new technology. And even when Jackie was talking about the curiosity of people wanting to know what's going on with this new probe on my property and looking at what's happening here, people are naturally curious. People want to know what's happening. They want to have line of sight of it and get directly involved. Thank you. Next slide. So we've been really lucky. Oh, that last one doesn't want to stay there. In working with United Utilities and many other water company partners in the latest round of OFWAT innovation projects, we've been awarded one which is called Catchment Systems Thinking Cooperative. Not a very user-friendly name, but that's the title of the project. But essentially, that is going to enable us to bring in citizen science and independently collected data to help give a much better informed and well-rounded picture of what's happening. Thank you. Next slide. And so what this project is going to do, it's the main objective of this is that when we have independently collected data, that can be defensible data that can then be incorporated into a national monitoring network. So we need to have standards and a structure for that, something that allows this data, allows us to have confidence in this data. The project is going to deliver 15,000 hours of volunteering across more than 1,000 square kilometres of catchments in the initial 8 demonstration sites. And sorry, my slides are going a bit mad. Is it possible to get back? I don't know if that's triggered an automatic follow-on. No? Okay, there we go. We've got lots of water company partners who are already involved, 12 of those, and other environmental NGOs and academics. And there's good resourcing for that to build up capacity at the local level and start putting the right instrumentation in place and developing these standards and frameworks. Next one, please. I hope it stays still. I'm sure that it's not the operator. I'm sure it's something in my slides. So I'll cut to the chase and get to the summary of this anyway. I think what's really exciting about this project, you can leave it on this last one, it's fine, is that this is the first time that we will have a national framework that helps to standardize citizen science approaches, enables everybody to get involved, but in a very structured way, with defensible scientific data that's giving a much more complete picture, that involves our local catchment-based partnerships, our local river trust members, and other community groups to start finding out what's going wrong in our rivers. And what's really important about that is not just getting the data, making sure that it's good data, but making sure that it's coming into a national framework that can then be used in decision making, both at a policy level as well as at a more local level around planning implications as well. So, you know, this is going to be open data that will then be available and visible to everybody. And of course, this is the first time that this is being done. We need to make sure that this is really sets a deep taproot and has some sustainable resourcing and financing to make sure that it can continue for the long term. And I think, this is the last slide, which was very determined to show itself slightly prematurely in the process. But I think that this is what we're working towards. Tell me and I forget. Show me, I might remember, but involve me and I will really understand. So this is a chance to start talking to everybody in the catchment, not just as customers or people who are influenced by the poor quality water that they're receiving, but those who are actively participating and involved as citizens of their catchments with something credible to say. Thank you.
And thank you, Christine. So Q&A, and thankfully we've got quite a long time for Q&A, which is brilliant. The big ask, Christine, what do you need? I mean, citizen science, when I looked into the Rivers Trust as part of this, I looked into the great work that's being done by the River Guardians, is it? Up in the Mersey area. I looked at that and went, wow, this is brilliant, absolutely fantastic. How do we expand this? Obviously, Casco is the way of doing that. But what's the big ask from? I mean, the water companies are absolutely in a place to help here. You have put their money where their mouth is. What's the big ask? You've got lots of water companies on this call. You've got the Environment Agency on this call. You've got OFWAT on this call. What's the punchline? What's the big ask here?
Yeah, I think, first and foremost, we're so pleased that this project has been given the go-ahead, and this is really going to enable us to kind of join the dots of all of these great local groups like the River Guardians, who've been doing excellent work, but a little bit in isolation. This is really looking now at scaling. How do we make this defensible, relevant and important at a national scale, and how do we bring everybody together to do that? It's been a tremendous convergence, I think, of both having all the great technology, the kind of technology that Rob was showing earlier, available at this time, at the same time, as we have this great willingness to participate and to really be involved in understanding the problems and helping to implement the solutions. So I think, the big ask from all of the partners who are already involved is, well, thank you, and let's kind of double our resources that are going into this as quickly as we can, to acknowledge that this is a space for innovation in the first instance. So let's afford ourselves a short period in which we have some freedom to fail and genuinely innovate, genuinely take some risks that we wouldn't normally take in our kind of day-to-day mandates and activities. But then to kind of, once we work out what's working, to really move towards scaling this up as far as possible. And for any of the water companies who are not yet involved in it, please do get in touch with us and, find out how you can help to scale this up in your area as well.
So, yeah, I think that's a big call to the water companies. Please get involved. And definitely. Absolutely. I know I've heard a lot. There's a lot of environmental information requests. I can see, why there's been a distrust in the water companies and the data that they're producing. I know Andrew Chappell in the chat's been saying, well, we've got the MCERT scheme, and we do, and that is that's an independent quality scheme, mainly centred around flow and mainly around wastewater flow at treatment works, although that's being expanded to inlet flow monitors, spills to storm flow monitors, and that's a step forward. I think really for me, we have to listen to the likes of yourselves and say, okay, there's a problem. We saw that with the Environmental Audit Committee yesterday. Everyone there going, there's a problem, we want to sort this out. So I'm hoping that everyone involved does say, we've got a great OFWAT scheme. OFWAT provided us, and the water companies, OFWAT came together and provided us a way of doing this, of financing this. Brilliant. Now let's take advantage of it. And I challenged in a round table yesterday, challenged a group talking about wastewater-based epidemiology and said, well, why don't we just do it? And it's being done, which is the action that needs to be taken. So we do have some questions. Jackie, it would be interesting to understand the economics behind this. Clearly, there are costs and benefits. Do you have any proposals to translate these into actual statistics in terms of numbers of blockages, flooding and pollution incidents prevented?
Hi, can you hear me? Okay.
Yes, can, Jackie.
Oh, okay, I wasn't sure. Yeah, what I'd say is I think we're sort of working through that at the moment, building up that picture. Definitely within ops, that's those sort of benefits are being captured. In terms of the economics, I think this will be funded through improvements in our efficiencies in our operational activity, by more targeted sort of sewer cleansing programs. Also, all the savings involved with responding to internal sewer flooding once it's already happened, compared to spotting those blockages up front and being proactive about clearing them. And yeah, I'd say that we're working through that benefits case and understanding it and building it, making it better to sort of continue that approach. Does that answer the question?
I think it does. I also remember the work that Yorkshire Water did probably 2 or 3 years ago now on the blockage timeline. Was it James at Yorkshire Water, and fantastic work. So I think this is just a build on that, which is brilliant. And the work that Yorkshire Water's done to understand where the blockages are happening is really important. So yeah, I can see what it's that cost avoidance, and I think cost avoidance has always been a problem where the industry hasn't really understood. But we heard, I think yesterday. Sorry, Jackie.
No, sorry to interrupt. I mean, it's. I think that's one of the challenges. Like, it's definitely harder to do a cost benefit analysis based on cost avoidance. Yeah. So. But that's.
And I heard yesterday, I think it was in the Environment Audit Committee, cost of blockages is about 200 million. I think that must be a more recent figure, because I know Water UK produced about 100 million in costs 5 or 6 years ago. So again, 200 million saved and spent on environmental improvements sounds a very nice way to go. I think really probably one for you, Rob. We've got monitoring in the Environment Act. Are we monitoring the right things? Because I don't think BOD's in there, is it?
Well, that's slightly contentious. I mean, as we're probably the only company that can do it, it would probably feel a bit unfair to name it. So, this isn't really about trying to make a corner for us. This is about making our rivers better, and that's it. So whatever we can do to do that, brilliant. It names, I think it's pH, conductivity, DO, and turbidity and ammonia. It might not be all of those. Mm-hmm. The reality is, they don't tell us the picture. Joe Bloggs sitting at home wanting to know his water quality in the river is going to get these parameters, and what's he going to think about those? The one that will really tell him, forget the rest because they're only indicative, is ammonia. But ammonia doesn't mean anything to him, and it doesn't always transpire that that's his best parameter. They need to measure something in something that means something to them. And the only thing that means anything to them is something that relates to the bathing water standards, which is coliforms. Okay, so if you're going to go for a parameter, that's the one you're going to go for. You can, I mean, the example I use is that you can put a DO probe in a river and it's all great, and it obviously takes 2 or 3 days to deplete the oxygen caused by wastewater, so that's not particularly very good. But you can aerate a cubic meter of wastewater to 100%. Does that mean it's healthy? No, it's not. So all these parameters, there aren't the people, the resources, or the time to investigate a situation with a unique characteristics of DO, pH, conductivity, and ammonia to say that's a pollution event and that's what this will mean. No, it won't tell you. So you're just, what you're going to do is make the problem worse.
You know where I come from, Rob, is I like to measure the right thing, and I like the information source to be right. And I've been quite public about how much it's going to cost. We heard Dom Shepherd earlier, and Dom was very much on the same wavelength as me, that we're going to need quite big infrastructure. We're going to need monitoring points. We're going to need a lot here. It's going to happen. It has to happen. Well, I think what we've got to do is listen to the public, listen to the environmental NGOs, listen to the scientists, listen to everyone, and monitor for the right thing. Now, I've got my opinions.
No. There's a good saying, isn't there? The customer is always right. Irrespective of what we think as further upstream, what have you, customer's always right. So ultimately, one way or another, we will have to deliver what they want, and it is a demand-driven situation. So we're a long way there, really, in some respects. I mean, the Scottish Water Framework, they wanted something that was completely off-grid. So it means technically you can put it anywhere you like. Okay, we can do that now. Okay, and you can measure multiple parameters. It's not a problem.
You can measure multiple parameters, but the only thing I would say is we've come onto this quite strongly. Defensible.
Yeah,
has to be defensible. Has to be a quality standard. Has to be independently auditable. Has to be right.
Exactly.
My fear is, it's a massive fear, and I think everyone would probably join me, if we don't put the right thing in place in the right way, we can produce data that quite honestly tells us the wrong situation. Now, that's not meaning that we shouldn't put in. Yeah, exactly. That's not meaning we shouldn't put things in, start putting things in now. But I think probably some of the debate is, what do we put on? Yes, DO will be appropriate in some situations. It's a relatively easy thing to do. Maybe it's redox instead of pH. Maybe it's ammonia. We've got to know about nutrient pollution. Actually, I would also say it's phosphorus, but then that's the complexity that increases. We've also got the river ecosystem classification regulations to think about. That's where I know it's probably been adopted into the Water Framework Directive, but that's where all these classifications, biological, chemical classifications come from. But what the right thing is, I don't know. And I'd
one of the
love
big questions will come straight out is the first question, certainly by the water companies and potentially anybody, is cost. And kit is not cheap, unfortunately. But like with anything, I mean, I saw in a chat earlier about CO2 sensors. Many years ago they were thousands of pounds, and now they're £10 from B&Q or wherever, right? That's going to happen. It will happen, but we can't just sit here and wait for that to happen and then say we'll deploy it, because we've already destroyed our environment. And so there are big wins. There will be ones and twos where you can put out here and there that will have massive wins and will make a big difference. And then when you have to start proliferating further down the network to get that sort of smaller scale, then you can start putting out the numbers out, because by that time they'll be a lot cheaper. So it's cost isn't really a big. I shouldn't think should be a big issue at this stage. I think it's getting started that's important.
I would disagree with you in some ways. I would 100% agree with you in others. We've got to start as soon as possible. We've got to start putting the right things in place, and that's going to take listening to the NGOs, having that debate in person. Cost is a factor, absolutely a factor, because what we don't want to do is put the wrong thing in, lose consumer confidence, lose people confidence. But equally, where I 100% agree with you is actually the cost of not doing something is even worse. And the environmental cost is tragic, is huge. And the impact that it has on everyone is huge. But again, one of the questions I wanted to ask Christine is the CSO map, wonderful piece of work, absolutely love it. What else, data-wise, would be good to come from the water companies? Is that more up-to-date data? Is that, to me, CSO map is great, comes from the water companies, but actually, I think the water companies can help more here to get a better refined situation out. Ideal world, real time, great. Obviously, that can be a while to happen. But yes, what is a dry spill? What is a spill in storm? What is I saw the River Guardian stuff. I saw the CSO map. Brilliant work. But how can the water companies help the Rivers Trust get a I'm not saying better picture, a more real picture out?
Well, I think, of course, one of the big things that we're missing in the current data set is that it's showing flow events and flow durations, but gives no indication of quality. So there's nothing in there around water quality. And I think that's really essential in terms of prioritizing the CSOs and the upstream drivers and problems that are causing the overspills on the CSOs to be tackled first and foremost. Because, of course, cost is a big constraint. So how do we and how do we all agree a prioritization process as well as a pace of that process for things being cleaned up sooner rather than later? So I think, water quality data is going to be essential. We've already seen amendments coming into the Environment Bill whilst it's been in the House of Lords now, requiring EDM data for CSOs, as well as upstream and downstream monitoring of the receiving water bodies, so river water quality itself, rather than just the event flow monitoring from the overspill site. So I think all of those are really essential elements that will help to build up a much better picture. But definitely in the first instance, to get an understanding of the water quality impacts, because, one of the pushbacks that we hear often is that not every CSO is overspilling raw sewage, in terms of foul water waste into our rivers. It's a mix of urban overflow as well as some sewage water. Well, then let's have the picture. Let's know, where is it the worst quality raw sewage that we're seeing on Panorama, etc. Where is that happening? And where may it be, much less impactful groundwater ingress, for instance? And we really need to have that prioritization process happening. So I think water quality is the next big kind of frontier as we start shifting towards real-time data as well.
So and I think 100% agree with water quality. It's, to me, the question is, what do we actually monitor? I actually also think one of the things I was thinking of when I was thinking of this is, okay, there's that, but also we're going to hear this afternoon about hyperlocal forecasting. We have, to a certain extent, this morning Jackie covered it with the work that Yorkshire Water's been doing with Siemens. Can we give a more refined view of what's actually happening? So if I'm the Environment Agency, I'm going to court and I'm taking a water company to court. I'm going to plot the CSO spill against flow at the treatment works against the actual rainfall in the area. So it gives me more of a refined picture of going, well, actually, Mr. Water Company, you were spilling in dry weather. Here's the evidence.
And, I think this was highlighted really. Yeah, it was highlighted very clearly to the Environmental Audit Committee by Professor Peter Hammond, who, sort of showed how the lack of correlation between rainfall and overspilling in his particular example, and the early spills and the dry spills, and the point that spilling was happening when plants were not yet at capacity for spilling. So, that kind of level of detail of the data, which, really, given the conditions under which overspilling is allowed, proving that spills are happening during extreme rainfall events should be part of the data requirement. And
I would agree.
I think that work has highlighted it. Yeah.
And to be honest, we're not far off that. We've seen this yesterday and today, the UMON 3, UMON 4 work that's happening right now. And so we're not far off that. The only thing I think that's missing from that is the rainfall data. And as we heard this morning, that's publicly available. So in some ways, why aren't we doing that? Water quality, 100% has got to be done. I don't quite know what. Actually, Rob, I think that you saying we're the only company that can do online bod, it's not really fair. I don't care. I don't care what's fair. What I care is what's best for the environment at the end of the day. So that may give somebody a good shove to develop something to compete with you. I'm sure you'd love that.
The more it's out there, the better, because it raises the cause.
Exactly.
Probably just something I'll just jump back to what Christine mentioned, and you've mentioned about rainfall. And this might be a little bit alarming, but probably to be expected. We actually put a monitor out, and we detected, we had a rain gauge as well, 14 millimeters of rain in 24 hours. All right. Not a lot. Okay. At work, spilt for 3 days. All right. Okay. Reported it to the Environment Agency. Okay. And didn't want to attend. And they turned up the next day and said, oh, there's no fish kill. So don't care. That's not the point. So even with rainfall data, it's not going to help. It's minds and attitudes and giving the Environment Agency backing to do something about it, because they haven't got the time, resources, and in some places the inclination to do it. Which is a shame.
I think again what we saw from the Environmental Audit Committee yesterday, culture. When I realising that whole thing, culture throughout the whole 3-hour piece. And so, and I think this actually, those who are interested, do join me on the net zero, because I know it's a different subject, but we have got a couple of Danish people on the net zero, and the cultural difference I see, this may shock you, but there's a Danish person I know very well, and I was having a chat with her. I did a piece of work for somebody about the technology, And I looked at it to the international perspective and spoke to this person I know in Denmark very, very well. And she said, well, actually, Oliver, this particular works, we haven't had a discharge consent for 15 years. The consent doesn't exist. And I said, well, how do you get anything done without a discharge consent? And she said, well, we know what we've got to do. We know what's environmentally right and environmentally responsible. So we just do it. And I turned around and went, wow, that's environmental responsibility just personified. And actually the Danish in particular are very good water stewards. And that's part of what's going to come up this afternoon in the round table. I also like the point of, if I go back however many years, polluter pays principle. And again, it was mentioned yesterday to a certain extent. Well, what would you think about paying per litre discharged, per litre spill? But basically paying on a polluter's pays principle. And that's where the water quality comes in. Now, some countries in the world do pay on the polluter pays principle. They pay per kilogram of BOD discharged or kilogram of ammonia discharged. Is that change in regulation that's needed? Perhaps. And again, it's a debate to be had. And of course, monitoring comes into that. But at that, I think we've come to the end of this session. Again, I think I could talk about this with the three of you for an absolute age. It's been an absolute pleasure, and I think a very productive session. So thank you, Jackie. Thank you, Rob. Thank you, Christine, for a wonderful session. For our audience, we're going to have a bit of a lunch break now. Do come back for our final session, where we're going to hear the work that Stormharvester's done on artificial intelligence sewer blockages, as well as the work that Ovarro has been doing on rising main burst detection. So again, those are things that Yorkshire Water have mentioned in this session. We're going to have some case studies of how we manage, of how we can use intelligence to at least do more. So thank you very much. Thank you very much for our panel in this session. In our final session, we've got some fascinating presentations by Brian Moloney of Stormharvester and George Heywood of Ovarro. We talked this morning about the need to measure and then how we measure. In this final session, we're going to talk about how we manage. We've always said all the way through, measure to manage. In this session, we're going to talk about how we manage, and we've got some great solutions that have been put into practice and how we manage the wastewater system. So in our first speaker is Brian Moloney of Stormharvester, and he's going to be talking about using artificial intelligence to detect sewer blockages. Brian, do you want to take it away?
Perfect. Thanks, Oliver. Thank you very much for that introduction, and delighted to be here and speaking and presenting to everybody on this topic. So what I'm going to do and what we're going to present here is a proof of concept project that we ran with Wastewater starting in 2019, where we were detecting blockages for them in real time using data from their existing sensor network, primarily their EDM sensors, their level sensors that they had across the network, focusing in the path area, and show you sort of the methodology that was applied and the results that were achieved from doing this. Before we do that, I'm just going to give you a brief introduction into what we do. Using 2 slides just to give you a little bit of an introduction into our company. So what we're all about is using hyperlocal rainfall forecasting, and this was touched on quite a lot earlier, and I'd like to actually bring some meaning to the word hyperlocal and what that actually means. What are we actually doing in terms of the forecasting, and then using machine learning, which are hyperlocal, to actually optimize across drainage networks. So we work in 3 different areas. We work largely around prediction, so predicting what's going to happen in real time. So doing machine learning to predict what's going to happen across your network in real time. Once you can predict, you can put thresholds and you can start to do analysis to understand, are we in the right situation with the sewers? Are the pumps working correctly? To actually layer a level of analysis around the machine learning. And the third one then is actually doing something with this, where you will actually go and take an intervention. So you'll preemptively, based on a prediction that you have, and based on the current situation in the networks, you'll actually go and take an action to improve the overall performance of the networks. Very quickly, I am just going to give a little bit about the company, just to see where we fit in the overall sort of industry and the different companies, different sizes. So we've about 5 years of research and development done in developing the methodology and the products that I'm going to show you now. That was really, a lot of it was with Queen's University in Belfast. And there's about £5 million of investment gone into it. We are very niche. We only work on wastewater and stormwater drainage networks. We have a collection of AI experts, machine learning experts, and drainage engineers. What I would like to call quite a lot of recovering hydraulic modelers, including myself in that bracket, where people that understand the domain, understand the industry, and pairing those people with the AI experts. We're working with quite a few of the UK utilities now, and you can see there that the awards, and which I think are verification for this new methodology of applying AI and ML to detect problems and provide solutions across the network. So enough about the business and enough about the company. What we're going to do for the next 15-20 minutes is talk about this project that we ran with Wessex Water, which really started off with them publishing a challenge to their marketplace in October 2019. And that challenge was, intelligent sewers, can we make alarms smarter? Really what Wessex Water had, was a challenge around blockages and detecting blockages in their network. Understanding when they got an alarm from their existing alarm network, was that genuinely a blockage or something that they could make an intervention on to make an improvement on the network? Or was it just high level because of rainfall or some other cause that didn't need an operational visit to site? You can imagine Wessex Water are managing about 35,000 kilometres of sewers. And from their own records, what they estimate is that they get about 13,000 blockages a year, and that's costing them, directly impacting them, about £5 million in terms of cleaning and jetting and getting the sewer back up to an operational condition. The difficulty that they have, and the reason they published this challenge, was to understand when and where those blockages are happening. If we can do that preemptively, even better, so that we can actually get out before the blockage, or once there's a restriction, before it forms a full blockage and a full pollution event, where we can actually get out and get out on site. And in this instance, not using a hydraulic model to this, using the data, using machine learning, hyperlocal rainfall forecasting to actually deliver this result and deliver this benefit. So what the trial entailed was, the proof of concept was running this system 3 months live on the catchment of Bath. The overall population in this area, I think, is about 200,000 people. So you were running it on about 10% of their overall network to see if this could be achieved across a 3-month period, where operational crews would actually be directed by the alerts that were given from a machine learning system to see if that could actually identify blockages and if that could actually get out and unblock sewers in real time. And I'm delighted to say that the results of the proof of concept, and spoiler alert for the end of the presentation, we were successfully able to do this. On the back of that 3-month proof of concept, we've actually moved now to a full network rollout, rolling this out on a 5-year contract across the entire wastewater network for Wessex Water. So not that often that you start off with a proof of concept project, looking at a 3-month trial, and then very quickly, within a year and a half, you're moving to a full network deployment, moving across the whole network. So I'm going to explain now a little bit of the methodology around that and the results that were achieved in that. Okay, so yeah, there we go. So how do we work and what do we do in the catchment? So essentially, we use our machine learning system to learn the behavior of the sewer network at all the censored points relative to any factor that could influence them. So you learn, the machine learning learns the behavior of the sewer network, the historic data, the historic level information, historic pump information, anything you have sensor-wise from the existing network. We used about 2 years of data to learn the behavior of the system. And then we used any influencing factor that could influence the level of the sewer. And we started off looking initially at rainfall, hyperlocal rainfall, and then we moved on. About 20-25% of the assets were being affected by infiltration, some of them being affected by boreholes and groundwater level. So we started to add into the machine learning feature sets different factors that could affect the river level to improve our predictions. And really, that's a critical point here, is that you're not just looking at hyperlocal rainfall, you're actually looking at borehole information to get an indication of groundwater ingress. You're looking at local river levels, if you've got any inflow coming in from the river levels, and anything as well as that, looking at on the tidal patterns. Not so much relevant to Bath, but since we've moved out of Bath and we've moved into different areas, particularly Bristol, you're seeing tidal patterns affecting the sewer performance and sewer levels at any point in time, and using that information to input into the machine learning model to help you predict what's happening in the sewers, so that we can identify in real time if we have an anomaly or if we have something that shouldn't be happening as it is. So the whole principle of the machine learning is to develop operational thresholds, so threshold windows that move dynamically, that indicate at what level the sewer should be at any moment in time. And on the next slide, we're going to show you a little bit about those actual dynamic thresholds and what they look like in practice when we get them implemented for the actual sewer. So just click on to the next slide. So you may have to strain your eyes a little bit just to see this. It's a little bit small. So on the graph on the right hand side, it's showing about a couple of days of operation of the sewer. So this is coming from an EDM sewer monitor, a level monitor that they had in the sewer. So we've built a system that cleans up the data first and foremost, that eliminates any dirty or inconsistent data from the sewer, because it's a pretty harsh environment to be monitoring in. So we've built a bespoke system that doesn't clean out the rainfall peaks, but cleans out anything else that can be indicating false data or incorrect data in the sewer network. So across that period, you can see then the diurnal pattern as the flow continues. And then you can see on the bottom in blue, you can see a rainfall spike. So that's the hyperlocal rainfall system. And then you can see how the sewer reacts to that. But the critical thing here is that the machine learning develops operational thresholds within which the sewer should be at any moment in time. And these thresholds critically are dynamic, and they move with factors like the time of day, the day of the week, what the hyperlocal rainfall forecasting is doing, what the local rivers are doing, what the local borehole information is doing. So it's taking all of this information to predict where the sewer will be or should be at an instantaneous moment in time. And you can see across that period of time, the dotted lines, if you can see them above and below the brown line, are the threshold within which the machine learning thinks that this sewer should be across at any moment across this period. And they start their lives as predictions. So they'll come as a 6-hour prediction. So we'll see a threshold in front of or ahead of time, which is basically predicting where the sewer should be. If the sewer level then in reality goes outside of its level prediction or its level threshold, that then is identifying to us that there's an anomaly, which in most cases represents a blockage or something that's happening in the network that's not consistent. So the old methodology here was that you would have a threshold, a static threshold at 80% or 90% or 100% that would go into alarm once you breach that threshold. We're moving away from that to a dynamic model where the machine learning can actually move the threshold and dynamically change a threshold in real time, so that you're not flagging up things like overflows or high levels because of rainfall, because the machine learning can see, okay, based on how this sewer has performed during every rainfall event in the last 2 or 3 years, depending on how long you learn the behavior on, it can predict that, okay, this is not out of sync with how this sewer has performed before, or how this monitored point has performed before, and therefore I don't need to flag an alert or an alarm. In the other instance, if you had the level increase and break the threshold, go above the threshold, in that instance, then yes, it is an anomaly. It's not consistent with how it's performed before, and in that instance, it has to it will flag an automated alarm that will go to the control room. That will then be investigated by the operational crew. And the key here is a condition-based maintenance system where you're trying to get the operational crews to the critical points in real time before you end up having pollution events across parts of your network. So in terms of the proof of concept that we ran, so I said earlier that we were working in the live system on the Bath network, on the Bath catchment. So they had 98 existing sensors in this catchment. The majority of them were EDM level monitors, some hydraulic monitors, I think we had 9 pumping stations, and there was 1 treatment works, out-of-town treatment works, where there was 1 level sensor into the treatment works as well. So all of these had their own machine learning model built for each individual point, and we were using the machine learning model at each point to flag up if there was an anomaly at any of the 98 points in real time, and then getting that information to the operational crews. I spoke before about the hyperlocal rainfall forecasts. So what we're doing is we're going 1 step beyond the kilometre or kilometre and a half or 2 kilometre square grid that you'll get from your standard Met Office output from an Outcast system. We're actually taking an individual coordinate. So we're doing a 3D interpolation on the hyperlocal rainfall as it exists. So we're not associating each asset with the centre point of the grid, a rainfall grid that it sits in. We're actually looking at a coordinate point and doing an interpolation on the 3D plane that the forecast is coming in to give us a point in time, to give us an actual coordinate point for rainfall file. So if you've got 2 assets that are 50 meters apart, you're going to get 2 different, very similar, but 2 different rainfall files for those assets based on the prediction and based on the system that we're running here. And we saw a significant improvement in our machine learning model accuracy scores when we did this, compared to when you just use the center point of the kilometre square grid or kilometre and a half grid, whatever you're getting in that location from an output from somebody like the Met Office. A really, really interesting development, and it was something that we could see quite clearly in the scores, that the prediction scores for the machine learning models would improve. And you'd get a better score when you had specifically got a point, as opposed to when you were looking at the center point grid, a center point of the rainfall grid. So 98 different assets and 98 different rainfall input files for each one that you're learning on. So it's quite a sophisticated change in terms of actually taking an individual point and an individual coordinate. And then in terms of the results that were achieved, then in terms of what we got. So every alert that we sent to Wessex Water was taken by the operational crews, and it was investigated, either a desktop investigation or a site visit if that was deemed to be required by the operational crews based on the data and the alert that was sent. And all of the numbers here are what Wessex Water gave us back, the report from the maintenance crews. So none of this is what we have sort of come up with. This is all the information that was given back to us by the Wessex Water operational crews, which was basically like an exam paper results, marked the results of an exam paper basically from the alerts that we gave them. So every single alert that we sent them, what did they find afterwards? Was it a valid alert? Did it add value to the business? So in order to track this and quantify it, we need to know what their starting point was. So they told us if we weren't operating across this catchment, they would have had about 35,000 control room alerts. So they were getting 3,500 control room alerts into the control room for this catchment for the 3-month period of time we were working on. Now, the majority of these are going to be in the alerts for high levels based on sewers, rainfall, high capacity in the sewer, and then basically a lot of alerts, a lot of alarms start to trigger. And big issue that they were having is that they weren't able to identify if something was genuine or if it was just at a high level because of the quantities and the flows in the sewers. So what we sent them was slightly different. So we sent them across the 90-day period, so we're looking roughly 90 days, 3 months, we sent them 136 control room alerts. So essentially you're sending them about 1.5 alerts a day, which is a manageable number of alerts that the ops crews were actually able to get out and investigate each individual one so that they could actually come to a conclusion whether that it was valuable or it wasn't valuable for the business. And then when they scored this for us, what they told us was of the 136 alarms that we sent them across this monitored 3-month period, there was 129 control room alerts that were genuine, that identified something that they didn't know about, and that they were alerts that they would want to have had and they wanted to investigate. So there was 92% accuracy on the alerting number that was sent. And basically, critically, what these alerts showed was that they identified 60 early forming blockages in real time that they were able to get out and investigate and unblock. That was critical, where they told us basically that there was at least twice, probably more, but at least twice when they got to site, when they thought they were about to incur a category 3 or worse pollution incident, if they hadn't have got the alert in real time to get out there. So the sewer was to a level where you were going to have a pollution event that they were actually able to overpump and avert because they got there in time. And that was all because we were able to send an alert when the threshold had been breached in real time, so we could get them out to site so that they could actually make an operational change and they could avoid the pollution and the spilling event. And what's quite exciting for us, if we look at this, we had no major pollution in this catchment across the period of time we were working there. We are now in the process of scaling this out across our whole network, and I really, really think we're going to make a significant difference in the number of pollution events that they have, particularly associated with blockages across the overall network across the next couple of years there when we're rolling out. So that's on the blockages, and that was sort of what they set out to achieve, was to validate that they could actually identify these early forming blockages in real time, get somebody out to site, make an impact, and they built a business case then around events that would have been categorized pollution events that they were able to avoid as a result of the alerts. Something that we identified through the trial that maybe wasn't foreseen at the start was this idea of being able to identify sensor faults or telemetry faults in real time. It actually surprised us and surprised Wessex as well, that when we were working across the catchments, there was 64 different times. So you imagine we're working on 98 different sensors for 3 months. There was 64 different times when the sensors went into a state where they weren't giving valid information back that could actually be used to make decisions. So it was a really, really important way of identifying when a sensor was operating correctly, when it was sending back the correct data that was usable, that could be interpreted, and that could actually be used for their reporting, but it could also be used for us in our analysis of the blockage identification of the blockages across the network. And this is quite an interesting one where they're talking about scaling up, and a lot of water companies are talking about scaling up to very, very, very big numbers on their sensor networks. But I think there's a note of caution here around quality instead of quantity would be our view on it. Because you can see there, if you've got 64 different times where you've actually got to go and investigate and either mobilize a crew or reset an alarm, then what you're going to have, if you have 20 or 30 or 50,000 sensors in your network, you're going to scale that up proportionally. And I just think a note of caution from our side when we were looking at that, I think it opened everybody's eyes on the trial to understand, how often that there was an intervention required to get part of the sensor network back up and running, and what that would mean if you had significantly bigger numbers across your overall sensor network. So in terms of the pollution events and what we were picking up, this is just one example of pollution event. And this is one of the really interesting ones. They averted a pollution incident here in the centre of Bath based on one of the alerts that we had sent them. And this is the data that was there at this moment in time. So what you see on the screen here, again, I think you've got about 15 days here of censored data. The brown is the sewer level, as you can see across this period of time. And you can see sort of halfway or maybe 3/4 along, you can see that there's a drop in the level, that there's an instantaneous drop in the level. And the machine learning had picked up for us that that wasn't a valid drop, that there was no reason why that sewer level should have dropped in the way it did. Now, what Wastewater told us was that they would not have picked that up if it wasn't for a system like ours, because they have 14,000 level monitors. They don't have eyes on them all the time, obviously. So a system like this that could actually monitor them all, put thresholds there and identify when they went above or below a threshold was going to be really, really useful. What we did is we sent an alert. I'm just trying to get the click on. Yeah, there we go. We sent an alert. Basically, the machine learning picked up the change in level, and we sent an automated alert on the back of that change at 9:30 to identify that there was a strange level happening, something strange happening in the sewers. The level had gone slightly below it should. And the reason we like showing this example is because we have a camera in the sewer at this point. So you see on the left-hand side was regular flow in the manhole. On the right-hand side was what we were picking up, which was based on the levels, a low flow. Now, usually water utilities or water companies, a low flow is not something that's going to be raising many alerts. It's a high flow that they're looking for, an 80% or 100% alarm. When they got out to site and investigated this particular alert, we instructed them based on our alert to go upstream and check upstream, because it looked to us like there was a potential for an upstream blockage. Once they went a couple of manholes upstream, what they identified was that the sewer was almost completely blocked and there was just a trickle flow getting down past. And what had happened was there was a non-return valve upstream that I've just shown there in the bottom right hand side of the screen, had basically dislodged. It had lodged itself in the pipe upstream and it was preventing flow from coming down. And this basically the build-up, they reckon, was about an hour or 2 hours away from being a pollution event or a pollution/flooding event, where they were likely to have, because it was just upstream of the CSO, they were likely to have pollution on the road and on the streets, and they were likely to have got a customer call about right outside a tourist area having some pollution. So quite a nasty event that we were able to avoid based on identifying a low level, which is quite interesting. Usually you're picking up a high level, but also using a two-way threshold to pick up a low level here. So that's just one good example, one really interesting example where you actually use the level data, you monitor it, you identify an alert or an alarm, and you get somebody out on site to remedy a problem which averts a pollution incident, which I think is quite powerful, particularly if you're able to move that out across the whole network like we are now. I think this is the last slide on my side, just to summarize essentially where we've got to as part of the proof of concept. So as I said, we started off engaging with Wastewater in October 2019 when they launched through the marketplace the Intelligent Sewers Challenge. Through last summer, we went through the 3-month trial. The system was maintained in operation after the trial based on the results that we got. And a couple of months ago, we've gone through a tender process and are now rolling out the system across the whole network. And I think what's testimony there to the system is, as you can see from the quote from Jody, who was the project manager or the lead from Wastewater for the project, was the methodology was set out. Could they use machine learning to predict blockage formations in the network? And would that allow them to intervene so that they could avoid pollution incidents? And really, in short, the technology worked and exceeded expectations, which I think is a real validation coming from the customer, coming from the client in this instance. So happy to take any questions, or if anybody wants to sort of contact directly, more than happy to take anybody through or answer any questions as we go here. So Oliver, I'll hand back. That's hopefully been informative and interesting, just to show some of the work there with Wessex Water.
Thank you very much, Brian. I've seen that before and marvel at. Yes, I think the industry is ready to use machine learning and artificial intelligence. And it's a great case study of how we should be doing things in some ways. So I think rather than have questions now, we'll allow George to take over, and then we can have some collective questions and discussions at the end. So George is from Ovarro, and he's going to talk about rising main burst detection in wastewater. Take it away, George.
Thanks very much, Oliver, and thanks, Brian, for that. It was really, really good, excellent work that you're doing there in the gravity sewer network. And my presentation links really well with that, because we're talking about, in many ways, a similar kind of solution, but applied to a different part of the wastewater network. So I'm going to be talking about preventing pollutions from rising main sewers, and using existing monitoring and cloud analytics. So first of all, just to check we know what we're talking about, on the left-hand side of this slide, we've got the gravity sewer network where the blockages are forming that Stormharvester are detecting. And ideally, that's all we would need in a wastewater network, because the catchment would drain nicely to the treatment works on the edge of the river. But in real life, often there are low points in the catchment where we need to install a pumping station to pump the wastewater out of that low point over a hill back into another gravity network, perhaps. And these wastewater pumping stations, they pump the water up that hill through a rising main, which is a pressurized pipe, just like water pipes in the clean water distribution network. But obviously, these are carrying sewage, and just like the clean water pipes, they do burst from time to time. But because it's sewage, it's a different kind of event, because we've got wastewater being pumped out into the environment, and that will often cause a pollution incident. And the way that these events are normally detected is this little chap here who's out in the early morning with his owner, and he smells something that shouldn't be there, and his owner becomes aware of this and gets on the telephone to the water company, or worse, the Environment Agency, and that's not what anybody wants to happen. And I think that more and more the water companies are wanting to be the first to find out about this kind of event, so that they can do something about it before it becomes a severe pollution incident. And that's what we're trying to do. So we're trying to answer this question here in the bubble there. So how can we detect rising main bursts more quickly, so that we can take rapid action to prevent environmental damage? So we're aiming to be able to detect them within maybe 30 minutes or an hour at the most, rather than waiting several hours until the next morning, or even in sometimes days or weeks to discover the event. So what's the problem? Why is this important? Obviously, environmental pollution is something that we all want to prevent. The events are categorized by the Environment Agency, and all the events that are categories 1 to 3 are classed as pollutions that need to be avoided. And in the current 5-year period in England and Wales, those events are subject to approximately £75,000 outcome delivery incentive, which means that water companies are penalised for each one of these events to that degree. They can also lead to property flooding if the rising main is near to properties, and there will invariably be clean-up costs that the company has to bear, costs of tankering, aeration to restore the river, and so on. There might be court cases, legal fees, and in the worst case, fines. There'll be Environment Agency enforcement undertakings, potentially, You might have to pay compensation to landowners. There'll be the costs of internal investigations and external investigations by the EA. There'll be PR costs because of the local media coverage, and there'll be potentially reputational damage. And that news coverage on the right there is just an example of some from an event in the Wessex Water area. Sorry, Wessex Water, not meaning to point you out. It's something that all the companies are suffering from. So how do we do this? We're using existing monitoring already in place at the pumping station. So this will almost always include pump status, so the times that the pumps are turning on and off. It will often include the level in the wet well. And in some cases, there will also be monitoring of pressure and flow, and that will be coming back through an existing remote telemetry unit into a central SCADA telemetry system. And the data look something like this. So you can see there that there is a blue line, which is the flow, and on the left-hand side, you can see the pumps turning on and off as the wet well fills and then empties. You can also see an orange line, which is the level in the wet well. So it's zigzagging up and down on the left-hand side, but then in the middle there, there's quite a serious rainfall event, and there's a period when the wet well is continuously full, and the level goes up quite a bit higher than normal. And then in this case, sorry, I'm just waiting for the clicker to respond. Never mind, I'll keep talking. Oh, it's gone too far. Bear with me. So on the right-hand side of that graph, which I think will come back in a second, there's some higher frequency oscillations which are caused by interactions between more than one pumping station on the same rising main. And the question we're trying to answer in all of this is, what would a burst look like? How, if we're with this monitoring data, what would we expect to see when a burst occurred? And that's really the first step that we had to take in developing an algorithm to detect these bursts automatically. And we've developed a product called Burst Detect. And it works by, as I say, using existing monitoring. And this is quite important because we don't want the companies to have to pay a large capital cost to go out and install additional monitors all over their network. We're using multi-tenant software as a service approach in the Microsoft Azure cloud. And that we've chosen that approach because it means that we can easily add a new customer to the system. There isn't an expensive and time-consuming IT project to set it all up. All that's needed is making a data connection from the company's telemetry system to our cloud, our secure cloud environment. Similar to Brian and his colleagues, we're using machine learning algorithms to do this, and alerts are coming out to the users by email when a burst is detected. We're aiming to add other alerting mechanisms as well, but at the moment it's emails. So just looking at a little bit about the machine learning algorithms. So as I say, the first stage is to understand the data, and then we need to cleanse it. We need to strip out the mess kind of from the real world data, so we can get a cleaner series that is easier for the machine learning algorithms to process. And then we transform this into a single time series signal that will allow us to easily pick out the burst events and then detect anomalies in that signal. So the story so far, we did a proof of concept project with one of the wastewater companies in the early part of last year, which that was using a very early version of the algorithm in an online implementation, and that gave us confidence that this was likely to work. We were able to show that we could detect bursts. We had a few more false alarms than we wanted to at that stage, but we thought we could do something about that. So we decided to go further. We did some product development work around the software interface for the users, and in parallel with that, we made those improvements to the algorithms, and I'll say a bit more about that soon. We then have gone through a series of offline trials with about 6 different companies so far, where they provided us with data. We analysed that data and submitted our results, a bit like Brian's homework being marked. They marked our homework and told us whether we succeeded in detecting the bursts that they had, and that those have gone really well, and several of those are now going forward into either live trials or a proper licensed continuing use of the software. So we've now got a portfolio of different algorithms that are applied automatically to the data according to suitability. So depending on which signals there are at a particular pumping station, the different algorithms get applied. The first one was using the maximal data set, so it was using pump status, flow, and pressure. And then because we were finding that a lot of the potential customers were saying that they only had flow and pressure data at a minority of their pumping stations, we started seeing how far we could go with reducing that data set. And we began first by dropping the flow data and looking at whether we could detect with just pump status and pressure. And we found that we could. So we went one step further and tried to do it with the pump status data only. And this was obviously really desirable because almost all of the pumping station stock have got pump status monitoring. And again, we were able to detect blockages just with the pump status data. It's perhaps a little bit less sensitive than the first algorithm, but it's still performing very well, we found. These have been tested now against a large data set, so it includes data from 6 companies and 85 different pumping stations, about 12 months per station on average, and more than 30 burst events. So I've just got a few graphs now that show you some examples of events from those trials, and apologies that these are kind of working quality rather than presentation quality, but hopefully you can see what's going on. So the blue dots there are flow, and the green dots are pressure, and the red and purple lines at the bottom there are the pumps turning on and off. And you can see in this case that there is something going on there in that yellow area, and we can zoom in a bit. And what happened was that Burst detected an event at that step change there in the blue flow data. It was detected at about 11:30 on the 22nd of January, and that was a severe pollution event that could have been avoided. And that was using algorithm 1, as I say. So looking at number 2 here is a little bit more subtle. And again, the blue dots in the middle are flow and the green ones towards the top are pressure. And we've put on some horizontal yellow dotted lines here just so you can see what horizontal looks like. And it's not that easy to see, but there is a small increase in flow over that period, and perhaps also a small decrease in pressure. And that's generally what the algorithms are looking for, is an increase in flow and a decrease in pressure. This one is very gradual, but because it's also very stable, it was possible to detect this. And we the algorithms issued an alert at about 10 to 2 on the 28th of June. And it wasn't until the 21st of July in this case that the company became aware of this event, because it wasn't particularly big and it was in quite a remote location. It was something they didn't find out about for quite a long period. Number 3 here. So in this one, we've got yellow flow data and green pressure data. And the pink vertical lines are the alerts that the burst detectors issued. So the first one associated with this event was there at that arrow. And the company became aware of it here a little bit later. And I think, sorry, I thought I had the times on there. It's a number of hours later, anyway, that the company became aware of that event. So going on to number 4. Now, this is where we start to drop the flow data and just be using algorithms 2 and 3. So what we do is that we generate estimated flow figures using the pump status information. And the blue and orange dots there are the estimated flows out of the pumping station, and the green dots are the estimated flows into the wet well. So you can see that the green dots are going up and down with a daily cycle. This is quite a long period, about a month of data. So if you look very closely, you can see a kind of daily cycle going on in the green dots. But then the blue dots, because the blue and the orange dots don't contain that daily cycle, because it's just the outflow from the pumping station, which is a fairly constant amount. And what happens is that we detect a burst here as those outflows begin to increase, and the company isn't aware of this event until there again quite some time later. So that it's a couple of weeks later before the company becomes aware of the burst in this case. And then the fifth and final one. This one is detected by the pump status only algorithm. And it's fairly easy to see from the data here where the event is. But again, this isn't real data. This is the estimated inflows and outflows that we're producing. And again, the company doesn't become aware until quite some time later. So 8th of February is when we alert, and then 18th of March, so over a month later, when the company becomes aware. So you can see from those examples that we're picking up the bursts often quite a long time in advance of current methods, and sometimes using a fairly small data set to do it. So just to give a little bit of summary of some of the offline studies. So number 1, study for company number 1, we had data for 28 sites, and these were all using flow pressure and pump status. And we detected a burst 4 hours before the current methods, and then another long-running burst over a month before the current methods. For company 2, we had 16 pumping stations. There were 2 bursts which we successfully detected, and one of those was 3 weeks before current methods. For company 3, 11 pumping stations, again for over a year, we detected 2 bursts, and this is a recent one where we were using the pump status only algorithm. So we're really pleased to see these results, and one of them was 3 days before the current methods. And then company number 4, we had 3 pumping stations, and there was a bit of a different mix of data between the pumping stations. So number 1 had a full data set, and we detected 5 bursts. This was a very bad rising main. Number 2, we detected 1 burst with pressure and status, and then number 3, we detected a burst with status only. So just to give a bit of a summary of the overall performance that we're seeing. So first of all, we're finding that about 70% of bursts are visible within the monitoring data. So that means that there's something there that can be seen by a human or by a machine. The other 30% are events that are generally too far up the rising main, too far away from the pumping station, and or too small in volume. And as a result, there is no hydraulic signature at the pumping station, so there's just no way that those are going to be detected by this kind of approach. But a lot of the majority of bursts we're finding are visible, and of those visible bursts, we can detect about 90% by our algorithms. And false alerts is really important because if it's going to cost too much to investigate all these events, then that's no good. We're finding that we're getting about one false alert per pumping station per year, and we're thinking that's about the acceptable level, and we're getting feedback from the companies to that effect. It's not that each one of these requires a visit to the site. What we're finding is that usually it just requires a very quick 2 or 3 minute inspection of the data by the user, and to determine whether it's appropriate to send someone out to site, and that very quickly eliminates any false alerts from requiring any more time spent on them. And the software makes that process very easy because the alert takes them straight to a screen that they need to see, and they can quickly diagnose what's going on. So a little bit of learning from the trials that we've done to date. So as I say, smaller bursts at the downstream end might not be visible, might not be detectable. Monitoring frequencies. So where we're using the flow data and the pressure data, we're finding that it works best with 5-minute or 1-minute monitoring. With 15-minute monitoring, it also works well, but it works less well where you've just got a small wet well and the time that the pump is turned on for is too short really to get a decent number of data points in that period. So we only need one data point in that period, but if we don't have any that for which we have one data point, then that's not going to work so well. When we're using the status only algorithm, this isn't so much of an issue because that's just reporting events. There isn't a monitoring frequency that is relevant. The workflow following the alert is going to be really important to achieving the benefits. And this is something that we're looking forward to the next stage and discovering more about how this is going to work within the companies. I think this is an area where Brian and his colleagues are ahead of us in the work that they've been doing at Wessex. So it's important to think about who is going to receive the alerts and how long is it going to take for them to review each one. And as I say, we found just a small number of minutes is enough. And then how effective is that review going to be in weeding out false positives? We think it's going to be very effective from what we're seeing, but I think that's something we're going to be looking for feedback from companies in the next stage. And the thing we particularly want to avoid is triggering unnecessary site visits. And then finally, we've found that it can be useful to be aware of any operational changes that are going on when interpreting those alerts. If there's some maintenance work going on at the pumping station, then it'd be good to know about that when you're looking at the alert that's coming in. Okay, so this is my last slide. So what's special about the solution that we're providing here? So first of all, it's focusing specifically on rising main bursts, which there isn't really much on the market that is doing that at the moment. And it's not requiring any additional hardware. It's aiming to work with a very wide range of monitoring setups, ideally to achieve 100% coverage of the pumping stations in a company. It's detecting the bursts rapidly and certainly a lot more quickly than current methods. It's easy to set up. And then the last one there, I think, will become increasingly important, because the bigger, as this begins to be used by more customers, we'll be gathering a larger and larger data set, and that data set will enable the algorithms to develop and provide better results, and also enable our data scientists to improve those algorithms as well as we go forward. And that's the end, Oliver. So I'll hand back to you, and very happy to have any questions.
So thank you very much, George.
I think you're on mute.
Fascinating.
You're fine.
Hopefully I've taken myself off. Yeah, that's right. Fascinating, and I think complementary solutions, to be honest. One on the gravity network in the main, and one on the pumping station network, on the rising main network. We do have a couple of questions from Jacquline, Diaz, Nieto from Yorkshire Water. What's the nature of the existing monitoring used for the approach?
So it's monitoring at the pumping station, pump signals turning on and off, flow monitoring at maybe 15 minutes, maybe 5 minutes frequency generally, and then and pressure monitoring. The status is the only one that's essential there. If you've got either one of the other two, then that will help, and we might be able to be a little bit more sensitive with those. But we're wanting it to work even with the minimum of the monitoring.
And I'll come back to that point in a second, to both of you actually. Does the approach give you visibility of rising main bursts along the full length of the main, or are there any blind spots that if bursts in a certain section, say the falling limb after a high spot, the monitoring won't see it? I think you've answered that actually in your presentation.
Yeah, certainly the kind of far end can be difficult to spot them. If you're going over the high spot, the falling limb, that's an interesting one. I think it should still. I think it should still be able to detect it. I think it will still be easier. So it will still be easier for the pumping station to pump along the rising main if there is a burst the other side of the hill, I would say.
Okay.
So yeah, I don't think that should be a problem. We haven't looked specifically at that case. We should do that, but I think it should. I think it should still work.
So probably be a question to both of you. In this AMP, the water companies are installing a lot of flow monitors at the front end of the wastewater treatment works. We've heard about FFT. For either of your solutions, is that going to help at all?
Sure, I'll take that first of all, then Oliver. I think it will help. The more data you have across the overall network, the better informed you're going to be, and the more trends you can pick up, and the more anomaly detection you can do across the overall network. So I think in terms of picking up blockages, it will help. Definitely, just the inherent nature of having more data, having more monitoring is going to help to detect more anomalies. I think not, no particular preference for exactly the solution we presented today for having monitoring at the inlet to the treatment works. It's just a general more monitoring is better. But obviously, as I pointed out with the sensors, there's probably a push point there that you would get to where you're better off having quality monitoring rather than just blanketing it with devices that are going to give you maintenance problems.
See, the ones at the front end of the treatment works, is you've got the UMON 3, UMON 4, they are going to be actively quality managed.
Yeah.
So they will be, and there'll be a known uncertainty. I know what we've seen from a lot of the digital twin solutions, and I'm thinking of it specifically, the one in Valencia, is they've had to, all right, it's been on the clean water network, but they've had to know the uncertainty of every single device. So there is that active knowledge of the data quality there, which I think is a fascinating approach. And I think probably throughout today, we've talked about quality, and we've talked about not misinforming. That works on the practical solutions that are out there, but also with the public outreach as well. And I think those are interesting points. We've got a couple of comments from Kathy Bora from Thames Water. One's to you, Brian. Great work preventing some pollutions. Really shows the direct environmental benefit that can come from this data, not just understanding our impact, but using it to actively intervene and prevent harm. Absolutely. Again, from you, George, to you, George, really great point about triggering unnecessary site visits and investigations. Data and insight is all very well and good, but we need to make sure we have the resource available to act on the information given. So no point in measuring if you're not going to manage to flip the analogy around.
That's right. And we've I think to help with that, we're making sure that we've got a good confidence rating on all the alerts that come out, so that they'll all come out with a percentage confidence rating on them. And I think that will help people to kind of calibrate their responses a little bit. So if they're finding that they're having to go out too much to things that are not real, or to review too many, then can use those confidence ratings. And we also have the facility to be able to adjust the sensitivity of the algorithms if we need to. And I think that's something that we'll learn from experience, in that we want to be sensitive, we want to be able to detect all the real events, but there is a little bit of a trade-off, isn't there, between sensitivity and false alerts.
And I think that's a very valid point, because if operations are being sent out to too many alerts unnecessarily, then there's a confidence loss there. I would say 5 years ago, if you start talking machine learning, artificial intelligence, it was starting to creep into some aspects of the industry. But quite a lot of people would say it's witchcraft, to be a bit flippant about it. But I think it's starting to get there. I've certainly seen it. And we've talked about big infrastructure changes this morning. We talked about the 200 billion that it would cost to separate the combined sewers at the minute. Absolutely vast sum. And if I do the finger and thumb calculation, it's going to be about 1,200 quid per household per year for the next 10 years. So not actually deliverable. Forget that, because it's not going to happen. We can't ask the customers, because no matter what the value, there'll be some customers who are on the breadline for that. Water poverty would go up through the roof. Not going to happen. But obviously we have to address the pollution problem. To me, there was a lot of work done on smart sewers, and a lot of work done on smart sewer networks, and they've looked at this. Do you think we're taking that first tentative steps towards smart networks?
I think we are. I think it is a first step. I don't know what you think, Brian, but the fact that more instrumentation is being put in sewer networks is beginning to pave the way for that. I expect we'll use in 5 years' time, we'll be using that some of that instrumentation for applications that we haven't even thought of yet.
Yeah, I totally agree. I think the more data you have coming back, the more processes you have to understand that data, the more what's capable around smart networks. And I think ultimately this is all moving towards automated control in time, where you'll have an automated system, and we might still be 10, 15, 20 years away from that, but you'll have an automated system as you would have in an oil refinery, where it's making decisions, opening and closing valves, managing flow through a network based on what's predicted over the next couple of hours. I think that's still something for the future, but I think these are all steps on that journey.
I know Southern Water put a smart network in a few years ago, and that was all related down to flooding. Their real challenge was sewer level monitors. Have you found the same there? You made an excellent point, Brian. Quality over quantity. And I saw the Environment Audit Committee yesterday. I've seen a lot of companies say, we're going to put 30,000 sensors into the sewer. We're going to put 20,000 sensors into the sewer. I personally makes me nervous, because I would agree with you. Quantity over quality. If you're not going to maintain an instrument, don't put it in. Seriously. And it's a hard enough environment in the sewer. Obviously, Wessex have put a certain amount in. What do you think again, I know I'm asking probably how long is a piece of string. What's the critical sort of sensor density?
So that is such a good question, Oliver. I think that is really the big question at the minute, and that's what we get asked regularly. I don't have a definitive answer to that. I think what you've got to do is you've got to work back from what your target is. So what are you trying to achieve? So are you trying to go to every single pollution event and every single blockage? In that case, you're going to need quite a coverage across your overall network. It's going to depend on things like topography. It's going to depend on things like pipe size. It's going to depend on customer behavior, how many blockages you usually get, where you get them. Have you done some hot spotting to understand, do they reoccur in the same areas? In which case, do we go and do we put some, do we cover some areas with sensors and leave others because we're more confident that we won't have blockages or pollutions in those areas? So what we can say is that we had 100 sensors in Bath, and we caught everything in that main network that we had. Now, that's not to say that in some of the laterals and some of the customer properties that, in really smaller sewers, you're still going to be having some problems there. So I think the answer to answer your question, Oliver, is what do you want to achieve? The sensor density needs to be planned around what's achievable. And if you do a business case for every single pollution event, pick up every blockage in every pollution event everywhere, is that actually going to stack up in terms of what you have to cost, and the upfront cost of the sensors, but also the maintenance cost of the sensors? I think that's really, really important, because it is such a harsh environment. We see in the sensor data that we're getting back that, you got null data that comes in regularly, and, this is all sensor providers. You get, spurious data, you get electrical interference. There's a lot of issues with the data coming out of that harsh environment. So I haven't really answered your question, and maybe George might as well.
Yeah, I think the thing that I'd add to that is that the locations need to be targeted on the basis of pollution and flooding risk. So some of the wastewater companies, UU for example, I know have got quite good risk models of their network, so they know the locations that have got the greatest likelihood of blockages. And they also know the locations where a blockage will lead to the greatest consequences in terms of pollution and flooding, and that enables you to do a kind of hot spotting of the places where it's most desirable to be able to detect an event.
It's interesting, and I know some of the others have. I've certainly had discussions, and I've certainly had those discussions. I was at the WWE innovation event, and we had a group of water companies there, and they were going, "Oh, this is what we want to do, but we know within the main network we've got to have a certain type of sensor. Within the lateral side of the network, we've got to have a certain type of sensor." So it was different. As you said, you've got to target what you want to do. Target what your objectives are, because again, it'll be different sensors for different areas within the sewer network, and it was quite interesting. And they were going, we want 50,000 sensors at 50 quid a sensor. Going, that's not going to happen. It's hotspot it, find out where your problem areas are, and then target those areas. And it always worries me when a company comes out, probably with the exception of hydrophones, because they're relatively simple, of saying we're going to install 50,000 sensors, and going, how many of them are actually going to be working after 6 months? So there is quality over quantity. Quality over quantity is absolutely very important. But probably the last question for me, if there was a technological sensor sensor that you wanted, a technological development that you'd like that would help your approaches, what would it be, if anything?
Yeah, that's a really interesting one. I think a lot of the limitation is coming from the data transfer. So majority of sensors that we see will report once a day at your EDM sites, any hydraulic level monitoring that's happening across the network, unless they go into certain alert conditions, in which case they go more into a real-time alerting. I think having more data in your hands more often than once a day is going to allow us to do more real-time analysis, which is going to give you maybe that 12 or 14 hours extra on the alert to get an operations crew there earlier, to make an intervention to event a pollution event. So to me, that would be the major development that I would like to see.
So it's mainly around communications protocols, really. George?
I think, well, I'm never going to argue against having more data, because I like to analyze the data, but I think from my perspective, I think there's still an awful lot that can be done with the monitoring that companies are already doing. Companies have got an untapped resource, I would say, in their existing monitoring, and that's kind of the philosophy that we adopted with the burst detect work, and I think it can be applied to other things as well. As what's the question we're trying to answer, and can we answer it from the data that we already have? I think that's the first question to ask.
So taking advantage of that data richness, information poverty, and making more from it. It's a great point. Yeah, absolutely great point. So at that, I think I'm going to say thank you very much to you both. You've given us, certainly, I think you've sparked some interest in some of our attendees. So it's been absolutely brilliant. I want to thank all of our speakers for today's Pollution Forum. I think we've had some really fascinating discussions, some real work, and there is a lot that we can do now, basically. We had Christine Colvin earlier, some great citizen science work, an OFWAT innovation challenge that's waiting for the companies to get involved. We've got solutions out there. Yes, there's going to be more. Yes, we've got to look to the river environment. And I think when I look to a lot of the companies that I've known over the years, some of them I've worked directly with, when you look at their philosophy. So I remember when I worked at Yorkshire Water, it was working with the water, making things better for the water environment for good. So when I worked for them 10 years ago, there was that want and need to be there to do that. I think there was a desire to come out of just the water industry and go more towards the holistic water cycle. Again, I work for Anglian Water, their catchphrase, love every drop. Again, the desire is to work much more holistically. We've talked about today, yes, there are monitoring challenges. Yes, there are questions to be answered. I don't think, to be honest, personally, I'll say it's my personal opinion, I don't think we've necessarily got the right monitoring solutions in the bill at the minute, but yes, we do have to look at it. Yes, the challenge to water companies, final effluent monitoring as a first step. And I know that's ambitious, I know that's a challenge, but guess what? We've got to reduce our environmental impact by whatever means. And actually, I think at the end of it, we may find there's a bit of a surprise that we can better that environment, and we can temper what we do at the minute, the way we work at the minute, because it's all linked in with the subject of our next round table, which is in about a quarter of an hour's time, about net zero. So do join us for that round table. We had a fascinating discussion yesterday on wastewater-based epidemiology. Next is net zero and how we can, again, monitor to manage. So thank you for everyone for coming. I hope you've enjoyed today's session. Thank you to all of our speakers, and look forward to further discussions in the future.